For centuries, Venus has been a planet of intrigue and mystery. Known as Earth's twin, it shines in our night sky, yet remains one of the most hostile places in our solar system. Back in 2021, the Bepi-Colombo mission, a joint project by the European Space Agency and Japan Aerospace Exploration Agency, made a fleeting visit to Venus. However, it was in April of this year that a reanalysis of the data revealed unexpected findings. There were oxygen and carbon ions leaking from the planet's upper atmosphere. These heavy ions, which are normally slow and difficult to move, were found accelerating at unexpected speeds. Scientists still can't figure out what the forces are behind this phenomenon. Is it an electrostatic wind? Or perhaps centrifugal processes have intervened. Venus has long been an object of exploration. Early missions such as Mariner 2 confirmed the absence of a magnetic field, and Venera 4 gave us our first glimpse of its thick, toxic atmosphere. Pioneer Venus Orbiter and Venus Express mapped previously unknown regions, but many questions remain. So how did Bepi-Colombo allow a more detailed picture to emerge? How did Venus lose its water? And why is its atmosphere so different from Earth's? And most importantly, could we survive on Venus? Today, we learn about the harsh realities and tantalizing possibilities of setting up a home with our mysterious neighbor. Venus's atmosphere is a complex and fascinating study. Composed mostly of carbon dioxide and sulfuric acid clouds, it starkly contrasts to the life-sustaining air we breathe on Earth. At Venus's surface, the pressure is 90 times Earth's pressure, and temperatures reach 869 degrees Fahrenheit. This incredible heat is the result of the greenhouse effect, trapping solar energy in the dense, opaque atmosphere. Our understanding of this hostile environment began with early missions such as Mariner 2, which first confirmed extreme surface temperatures. The Venera 4 spacecraft made deep measurements, revealing a dense carbon dioxide atmosphere and the presence of sulfuric acid clouds. The Pioneer Venus Orbiter mapped the upper atmosphere, showing the dynamism of Venus's weather systems and the presence of thunderstorms. Then came Bepi-Colombo. During flybys, the spacecraft penetrated previously unexplored regions of Venus's magnetosphere. Its instruments detected positively charged oxygen and carbon ions being carried away from the upper atmosphere. These findings were unprecedented because heavy ions like these are usually slow-moving and difficult to dislodge. The output of these ions testifies to the complex interaction between the solar wind and the atmosphere on Venus. Unlike the Earth, which has a strong intrinsic magnetic field, Venus has only a weak-induced magnetosphere created by the interaction of the solar wind with its atmosphere. This makes Venus more susceptible to atmospheric destruction by solar particles. Now, for the most startling fact, a comparative study of water loss by Earth and Venus was conducted. Both planets, according to scientists, started with the same amount of water. However, Venus's proximity to the Sun and its lack of a protective magnetic field allowed solar radiation to break down the water molecules in its atmosphere. Hydrogen, being the lighter element, escaped into space, while oxygen remained, contributing to the dense carbon dioxide atmosphere we see today on Venus. By contrast, Earth's strong magnetic field has protected its atmosphere, preventing significant water loss and enabling the development of life. The striking difference emphasizes the importance of magnetic fields for planetary habitability. Understanding the atmospheric mysteries of Venus not only provides a glimpse into its past, but also serves as a kind of precautionary measure for us on Earth. Okay, a bit of history for context. Space missions have been the cornerstone of our understanding of Venus. Each mission, with its unique capabilities, has contributed to unraveling the planet's mysterious environment. The journey began with Mariner 2 in 1962, the first successful mission to another planet. Mariner 2 confirmed the extreme surface temperatures of Venus and established the absence of its own magnetic field, setting the stage for future explorations. In 1967, the Soviet probe Venera 4 made the first direct measurements of Venus's atmosphere. It detected a dense carbon dioxide atmosphere with clouds of sulfuric acid and provided us with the first data on the ionosphere. The Pioneer Venus orbiter, launched in 1978, began systematically mapping different regions of Venus's atmosphere, providing extensive data on its composition and dynamics. It confirmed the presence of heavy ion streams and helped identify the bow shock and magnetosheath formed by the interaction of the solar wind with Venus's atmosphere. The Venus Express mission, launched in 2006, built on these results and used the Space Plasma and Energetic Atoms Analyzer to study ion emissions in detail. It measured the absolute number of hydrogen, helium, and oxygen ions escaping, providing important insights into atmospheric loss processes. In August 2021, BepiColombo, a joint mission of the European Space Agency and the Japan Aerospace Exploration Agency, made its second flyby of Venus. This spacecraft penetrated previously unexplored regions of Venus's induced magnetosphere. The Mass Spectral Analyzer and Ion Analyzer detected cold oxygen and carbon ions escaping from the atmosphere. These ions were detected at a distance of about 6 planetary radii in a previously unexplored region. Among the departing ions were O-positive and C-positive, the latter being the first to be seen escaping from Venus's atmosphere. This indicates a complex interaction between the solar wind and the induced magnetosphere of Venus. Unlike Earth, which has a strong magnetic field of its own, Venus has only an induced magnetosphere, formed by the interaction of the solar wind with its atmosphere. The induced magnetic field is comet-shaped, creating a magnetosphere in which solar wind particles are slowed down and heated. BepiColombo's observations of the ion ejection mechanisms in this region have provided new insights into the processes that are inexorably destroying Venus's atmosphere. Understanding these mechanisms is critical to understanding the evolution of Venus's atmosphere. In particular, the process of losing its initial water concentration. The quest to understand Venus involves not only studying its hostile environment, but also looking for the potential of life in the most unexpected places. Even in Venus's harsh atmosphere, scientists are searching for the fundamental components of life. High-tech experiments aim to study Venus's atmosphere in search of evidence of life-supporting molecules. The discovery of phosphine gas in the upper atmosphere of Venus in 2020 has sparked intense interest. On Earth, phosphine is associated with biological processes, leading scientists to wonder whether similar processes could occur on Venus. However, the harsh conditions on Venus complicate this search because of the extremely high surface temperatures and immense atmospheric pressure. Any potential life forms must be incredibly robust and resilient. Despite these challenges, the search continues. NASA's upcoming missions, Da Vinci and Veritas, aim to delve deeper into the atmosphere and surface of Venus. The Da Vinci mission will focus on measuring atmospheric gases, including the presence of any of the so-called noble gases and other elements, from the top of the atmosphere to the surface. These data will help scientists build new climate models and study the chemical composition of the atmosphere in more detail. The Da Vinci lander will provide unprecedented insight into the composition of the atmosphere and possibly detect molecules that may be precursors to life. These measurements will be critical to understanding the habitability potential of Venus and other similar exoplanets. The Veritas mission, on the other hand, will create high-resolution maps of Venus's surface. By studying the planet's geology and topography, scientists hope to discover signs of past volcanic activity and water flows, which would be important clues to understanding Venus's history and its potential to sustain life. This detailed study of Venus's surface and atmosphere helps astrobiologists improve their models of planetary habitability. Venus provides an instructive example. Despite its similarities to Earth, its environment has taken a radically different path. Understanding these divergent evolutionary paths may help us in our search for habitable worlds beyond our solar system. Venus and Earth, often referred to as sister planets, have striking similarities in size, mass, and composition. However, their environmental and atmospheric conditions could not be more different. Venus's atmosphere consists mainly of carbon dioxide and nitrogen, with clouds of sulfuric acid, creating a dense, toxic blanket. Earth's atmosphere, in contrast, is composed mainly of nitrogen and oxygen, supporting a variety of life forms. Atmospheric pressure on Venus is about 90 times higher than Earth's, which is approximately equivalent to being underwater at a depth of 3,000 feet or 900 meters. The greenhouse effect is extreme here. Solar radiation penetrates through dense clouds, heating the surface, but a dense atmosphere of carbon dioxide traps this heat, resulting in a surface temperature of about 869 degrees Fahrenheit, 465 degrees Celsius. On Earth, on the other hand, the greenhouse effect is in a delicate balance that maintains temperatures suitable for life. There are also several fundamental differences between the two planets, in addition to their proximity to the Sun. Earth has a relatively fast rotation period of 24 hours and a stable axial tilt, which promotes even heat distribution and supports seasonal changes. Venus, on the other hand, rotates slowly and in the opposite direction of most planets in the solar system. It has a rotation period of 243 Earth days. This slow rotation and lack of significant axial tilt results in minimal temperature fluctuations between day and night. The slow retrograde rotation contributes to Venus's extreme weather patterns and thick, super-rotating cloud layers that circle the planet every 4 Earth days. These clouds reflect a significant amount of sunlight, giving Venus a bright appearance, but also trapping a tremendous amount of heat. Geologically, both planets have volcanic landscapes. But whereas on Earth tectonic activity recycles carbon and supports a diverse climate, the surface of Venus is dominated by vast volcanic plains and high-altitude regions. The lack of tectonic plates on Venus means that heat is stored beneath the crust until it's released by catastrophic volcanic events, reshaping vast areas of the planet. The presence and loss of water are crucial factors in the different evolutionary paths of these planets. Measurements of the ratio of deuterium to hydrogen in Venus's atmosphere indicate that the planet once had a significant amount of water. The high ratio suggests that the lighter hydrogen was lost over time, while the heavier deuterium remained, indicating an historical loss of water. The different evolutionary paths of Venus and Earth give rise to the realization that the planet may be habitable. Venus's proximity to the Sun probably created a greenhouse effect that vaporized all the oceans and led to its current inhospitable state. Earth, which is at a moderate distance from the Sun and has a protective magnetic field, has retained liquid water and a stable climate favorable to life. As we enter a new era of space exploration, several ambitious missions are about to reveal more of its secrets. The European Space Agency's Envision mission, scheduled for launch in 2031, is designed to provide a comprehensive understanding of Venus from its core to its outer atmosphere. Envision will build on the discoveries of previous missions, such as Venus Express, which have hinted at volcanic activity and will offer a detailed understanding of Venus's geological and atmospheric processes. Envision will carry an extensive suite of instruments designed for a comprehensive study of the planet. Synthetic aperture radar will map the surface at resolutions of up to 10 meters, revealing details about surface texture and geological activity. Its subsurface radar sounder will penetrate up to a mile below the surface, searching for underground structures and layers. 3 spectrometers, Venspec-U, Venspec-H, and Venspec-M, will analyze trace gases and look for volcanic gas plumes and map surface composition. The Gravity Radiological Experiment will use radio waves to study the planet's internal structure and atmospheric properties. Envision will help unravel how geologic processes, such as volcanism and tectonics, affect the planet's atmosphere and climate. This integrated approach will provide clinical data to answer long-standing questions about Venus's past and present geologic activity and the dynamism of its atmosphere. India's Chakrayaan mission, led by the Indian Space Research Organization, is another important addition to the exploration of the planet. Planned for launch in the early 2030s, the probe will study the atmosphere and surface of Venus using a suite of advanced instruments. Instruments will be installed on board to analyze cloud layers, atmospheric composition, and features of the planet's surface. Using infrared and ultraviolet cameras, the spacecraft will study the dynamics of Venus's dense cloud cover and the interaction of the atmosphere with the surface. One of Chakrayaan's main goals is to understand the sulfur cycle on Venus, which plays a crucial role in the chemistry of its atmosphere. By studying the distribution of sulfur compounds and their interactions with other elements, the Chakrayaan mission will contribute to our understanding of the complex atmospheric processes on this yellow planet. These missions have potential to revolutionize our understanding of Venus. By combining data from Envision, Chakrayaan, Da Vinci, and Veritas, scientists will have a complete picture of the geologic and atmospheric evolution of Venus. These missions will provide crucial data on volcanic and tectonic activity, atmospheric composition, and surface interactions, helping to build a detailed picture of the planet's past, present, and even its future. Data from these missions will also help us understand planetary habitability and the conditions necessary for life. By studying Venus, we'll be able to improve models of atmospheric and geologic processes, which will improve our ability to identify habitable environments on exoplanets. Looking to the future, the ultimate goal of Venus's exploration is to pave the way for future human missions. Although the planet's extreme conditions pose significant challenges, advances in technology and a better understanding of the environment may one day make planetary exploration possible. Future missions could include robotic explorers capable of withstanding the harsh conditions of Venus's surface and then develop habitats that would protect humans from the intense heat and pressure. These habitats would then be equipped with advanced life support systems, allowing for longer stays on the planet and more in-depth scientific research. Exploring Venus is not just about exploring our nearest neighboring planet. It's also about pushing the boundaries of what's possible in space exploration. By overcoming the challenges of Venus, we'll be able to develop the technologies and strategies that will be needed to explore other extreme environments in our solar system and beyond. In the vastness of our solar system, beyond the belt of asteroids and gas giants, lies a world shrouded in mystery. Neptune, the 8th planet from our Sun, a distant ice giant, has long captured our imagination. For decades, we've imagined it as a dark blue sphere at the edge of our cosmic neighborhood. But what if the vision of this distant world was an elaborate illusion? This mysterious planet, named after the Roman god of the sea, has hidden its true colors from us. Cloaked in a shroud of deep blue, Neptune has been the subject of many stories and scientific investigations. But recent discoveries have removed this azure facade, revealing a reality far more complex and fascinating than we could have imagined. For years, our telescopes have been pointed at this distant giant, capturing its essence in pixels and data. What we saw, however, was not the reality of the planet, but a reflection of our own technological and perceptual limitations. The deep blue color we associated with Neptune was actually the result of our own interpretations and enhancements, a story we unwittingly created and believed. Today, we invite you to explore Neptune like never before. Delve into its true colors, understand its dynamic atmosphere, and unravel the secrets of its moons and rings. Centuries, Neptune was portrayed as a dark blue world whose color reflected its cold, distant nature in the solar system. This representation, deeply ingrained in our collective consciousness, has become the cornerstone of our understanding of this icy giant. But what if this image was a reflection of our perceptions rather than the planet's true appearance? Neptune's color is a story of scientific evolution and the search for truth. It begins with the Voyager 2 probe launched by NASA in 1977. Sent to the outer reaches of the solar system, it took the first close-up images of Neptune, painting a picture of the planet awash in a stunning blue color. However, these images were not a direct window into the true color of Neptune. In fact, they were interpretations, the result of processing the data through the lens of human understanding and the technological capabilities of the time. The deep blue color we saw was the product of enhancements made by scientists to emphasize certain features of the planet. This story began to unravel with the advent of more advanced telescopes, such as the Hubble Space Telescope and the Very Large Telescope. These instruments, equipped with state-of-the-art technology, allowed astronomers to see the true color of the planet again. The results of this study were striking. The new images revealed that Neptune's color was not the previous deep blue, but rather a more muted and varied shade. This discovery was not just aesthetic, but a fundamental shift in our understanding of the planet. The reason for this color misconception lies in the way we process and interpret astronomical data. Colors in space images are often enhanced or altered to emphasize certain features, or to make them more distinguishable to the human eye. In the case of Neptune, these enhancements over time have led to a collective opinion of its deep blue color. So, what led to this discovery? The key lies in a meticulous study entitled Modeling the Seasonal Cycle of Uranus's Color and Magnitude and Comparison with Neptune. This study, led by Patrick G.J. Irwin of Oxford University, along with a team of experts, set out to unravel the mysteries of Uranus's seasonal color changes. However, their journey will inadvertently shed light on the true colors of Neptune, disproving long-held beliefs. The team carefully analyzed a huge array of data obtained from Lowell Observatory over 6 decades. These data, supplemented by Hubble Space Telescope observations, produced a detailed picture of Uranus's disk-averaged color and photometric magnitude, revealing the complex interplay of its seasonal changes. One of the most important aspects of this study was the focus on the reflectivity of Uranus and the abundance of methane. The researchers unraveled a complex relationship between the lower methane content at polar latitudes and the different reflectivity of aerosol particles. This complex interaction of elements in the atmosphere of Uranus was thought to be influenced by the presence of methane ice particles, adding a new layer of complexity to our understanding. In parallel, the study allowed for a fascinating comparison with Neptune. Contrary to popular belief, the difference in blue hues between Neptune and Uranus was less pronounced. This discovery was the result of a critical reassessment of Neptune's color, disproving the image of deep blue that had been ingrained in our minds. The methodology used by the team was a combination of quantitative analysis, atmospheric modeling, and advanced spectroscopic observations. They converted measured reflectance spectra into radiance spectra, and then into tri-stimulus values. This process mimicked the visible colors of the planets as perceived by the human eye, bridging the gap between the raw data and our visual interpretation. The use of advanced telescopes such as Hubble and the Very Large Telescope played an important role in this endeavor. These technological marvels allowed the team to revisit and re-examine the true colors of Uranus and, by extension, Neptune, with unprecedented accuracy. As we delve deeper into the mysteries of Neptune, we find ourselves amid a maelstrom of atmospheric activity, in stark contrast to the relative calm of its stellar neighbor Uranus. Neptune's atmosphere, a turbulent and dynamic formation, is home to some of the most extreme weather in our solar system. One of the most striking features of Neptune's atmosphere is the presence of colossal storms, the most famous of which is the Big Dark Spot. Discovered by the Voyager 2 spacecraft in 1989, this massive storm, similar to Jupiter's Great Red Spot, is a testament to the turbulent nature of the planet. A large, dark spot, a giant rotating storm, is a window into Neptune's intense atmospheric dynamics. These storms are caused by the strongest winds in the solar system, reaching speeds of up to 1,300 miles per hour. However, to this day, the power and magnitude of these winds are a mystery to scientists, raising questions about their origin and the energy sources that drive them. In contrast, neighboring Uranus is a picture of tranquility. Its atmosphere, although composed of hydrogen, helium, and methane, does not have the same violent storms and extreme winds as Neptune. The difference in atmospheric activity between these two ice giants is one of the many mysteries of our solar system. Another intriguing aspect of Neptune's atmosphere is the presence of unusual hotspots, where temperatures can reach a staggering 750 degrees Kelvin. These hotspots represent a paradox because they exist on a planet so far from the Sun. The source of this heat remains a mystery, but theories suggest it could be caused by internal processes, such as auroras or magnetic reconnection in the plasma layers. The origin of these hotspots and the extreme weather conditions on Neptune are the subject of ongoing research. They force us to seek new answers to questions about planetary atmospheres and hint at complex internal processes that have yet to be understood. Stepping outside Neptune's turbulent atmosphere, we enter a realm of celestial harmony where moons and rings swirl around this icy giant. Turning our gaze to Triton, Neptune's largest and most intriguing moon, we discover a world of seasonal changes and atmospheric mysteries. Triton, a unique moon with a retrograde orbit, was the last solid object visited by the Voyager 2 spacecraft during its historic journey through the outer solar system. Because of its retrograde orbit, indicating that it was captured by Neptune's gravity, Triton stands out among the moons of our solar system. Its surface, covered in nitrogen ice, is geologically young and active, with dark green streaks indicating the presence of geysers spewing nitrogen gas. Triton's thin atmosphere, whose thickness varies with the seasons, is a fascinating study in extraterrestrial meteorology. Observations with the European Southern Observatory's Very Large Telescope have revealed that Triton's southern hemisphere is in the height of summer. This distant moon, despite its relative distance from the Sun, is experiencing significant atmospheric changes. The heat of the summer sun causes the thin layer of frozen nitrogen, methane and carbon monoxide on Triton's surface to sublimate into gas. This process causes the icy atmosphere to thicken as the season continues in Neptune's 165 Earth-year orbit around the Sun. The season on Triton lasted more than 40 years, and the southern summer solstice occurred in 2000. The discovery of carbon monoxide in Triton's atmosphere, as well as the confirmation of the presence of methane, marked a significant advance in our understanding of this moon. The presence of these gases, especially the enrichment of ice with carbon monoxide in the upper surface layer, feeds the atmosphere and determines its seasonal dynamics. These findings required a revision of Triton's climate and atmospheric models. The complex interaction of nitrogen, methane, and carbon monoxide not only determines atmospheric conditions, but also provides insight into the geologic and climatic history of the moon. But Triton is not alone. The planet is accompanied by a retinue of smaller moons, each contributing to our understanding of this distant world. These moons also show seasonal changes and provide insight into the complex gravitational interactions and environmental conditions around Neptune. When we turn our gaze from the moons to Neptune's rings, we encounter another aspect of this planet's mysterious nature. Neptune's rings, made up of a mixture of dust and ice particles, are dull yet mesmerizing. They testify to the planet's dynamic history. Scientists believe they're remnants of moons that were destroyed by collisions or torn apart by Neptune's gravity. The composition and characteristics of these rings are closely related to Neptune's true color and atmospheric phenomena. The subtle hue of the rings, which were affected by light scattering in Neptune's atmosphere, add another layer to the planet's color palette. The rings, reflecting and refracting light from the Sun, create the overall appearance of Neptune seen from afar. In 2022, the James Webb Telescope captured the clearest view of the rings of this distant planet in 30 years. Photographed with unprecedented clarity, these rings have changed the way we think about this distant planet. The most striking thing about the new Webb image is the clear view of Neptune's rings. Some of these rings, dim and dusty, have not been detected since the historic Voyager 2 flyby in 1989. The Webb telescope, with its enhanced capabilities, has brought these elusive rings back into focus. Neptune's rings are made up of several bright and narrow, as well as fainter dust bands. Infrared imaging by the Webb telescope has put these rings in a new light, revealing features that were previously hidden in the darkness of space. This is the first time these rings have been seen in the infrared spectrum, providing new insights into their composition and behavior. Neptune's rings, like the planet itself, are characterized by a unique composition. Unlike the gas giants Jupiter and Saturn, Neptune is an ice giant, rich in elements heavier than hydrogen and helium. This composition also reflected in the planet's signature blue color in visible wavelengths caused by a small amount of methane gas. In infrared images taken by Webb's NIRCam, near-infrared camera, Neptune does not appear blue, in contrast to the darkened appearance one would expect due to methane absorption of light. In infrared images taken by the Space Telescope, Neptune appears as a luminous, glowing white sphere. This absorption also affects the appearance of Neptune's rings, as they reflect and refract light traveling through the planet's atmosphere. This unexpected brightness in the infrared is the result of a unique interaction between the planet's atmosphere and infrared light. While methane gas absorbs red and infrared light, high-altitude clouds in Neptune's atmosphere reflect sunlight before it's absorbed. These methane ice clouds appear as bright streaks and spots that cast a ghostly glow on the planet in the infrared spectrum. By the way, you may wonder why Triton looks like a dazzling point of light, adorned with shining spikes, as opposed to the more subdued image of Neptune. These diffraction spike patterns are a characteristic feature of the imaging telescope. They're not physical structures, but rather optical artifacts created by the telescope's design. Light from Triton passing through the mirrors and telescope structure is diffracted, resulting in these striking peaks emitted by the moon. Diffraction, in simple terms, is what happens when a wave, such as light, travels around the edge of an object or through a small opening. Imagine light in the form of water waves flowing through a narrow slit in a wall. When the waves pass through the slit, they diverge in different directions, instead of just going straight through. This propagation of waves after passing through a hole or around an edge is what we call diffraction. In the context of the James Webb Space Telescope and its images, diffraction peaks arise because of the way the mirrors and structure of the telescope are arranged. When light from a bright object, such as a star or Triton in images of Neptune, enters the telescope, it's bent slightly by the edges of the mirrors and other parts of the telescope. As a result of this bending, the light diverges and forms the star-like spikes we see in the images. The study of Neptune's rings, especially in the infrared, provides valuable insights into the atmospheric conditions and internal composition of the planet. The interaction of the rings with Neptune's atmosphere, particularly the methane ice clouds, provides insights into the planet's climatic and environmental processes. The bright equatorial band that girdles the planet hints at the global atmospheric circulation, a key driver of the planet's winds and storms. The atmosphere, which sinks and warms near the equator, glows more intensely in the infrared than the cooler gases that surround it. As we conclude our journey through the mysterious world of Neptune, we reflect on the impact these discoveries are having on the broader field of planetary science and exoplanet exploration. Neptune, once a distant blue spot, is now a testament to space exploration's dynamic and ever-evolving nature. Discoveries concerning Neptune's true color, its atmospheric phenomena, and the intricate details of its rings and moons go far beyond our solar system. They provide a crucial example for understanding similar ice giants and exoplanets in the far reaches of our galaxy. The insights gained from Neptune will help astronomers decipher the mysteries of these distant worlds and enrich our knowledge of the universe. As we continue to gaze into the cosmos, Neptune reminds us of the limitless potential for discovery. Its example encourages us to keep looking, asking questions, and unraveling the mysteries of the universe. Reality. We think we know what it is. The ground beneath our feet, the air we breathe, the world we see. But the deeper we look, the stranger it becomes. Did you know that what we perceive as solid matter is mostly space? The atoms that make up everything around us are 99.9% space. In addition, there is time. It's not a constant, ticking away in the background. Time can stretch, slow down, and even stop under the right conditions. So how much of what we experience is real, and how much is just a construct of our minds? What if the reality we trust is just a shadow of something deeper, stranger, and infinitely more complex? What is reality? For the first humans, the answer was simple. Reality was what they could see, hear, touch, and smell. The world around them was interpreted through their senses, guiding them through every day. The rustling of leaves signaled the approach of a predator. The distant crack of a branch indicated prey. And the sensation of warmth from a campfire chased away the cold night. This sensory reality was everything. Survival depended on it. Sight, hearing, touch, smell, these senses were the tools with which they cognized their environment. But for them, reality was limited to that which was accessible to direct perception. The invisible world beyond their senses was incomprehensible. Everything tangible became real. If a sound was heard, the danger was near. If an odor was smelled, food could be found. If something could not be smelled, it might not exist at all. Survival was a continuous process of interpreting these sensory cues, often in life or death situations. Recognizing the difference between the roar of a predator and the rustle of the wind could mean the difference between safety and death. Early humans lived in a world where reality was directly related to their immediate needs: food, shelter, protection. For them, reality was not questioned, it was lived through experience. However, as society evolved, the concept of reality also changed. The question of existence and meaning began to extend beyond the immediate environment. What lies beyond the senses? What forces shape the world? Over time, the limitations of direct perception have given way to imagination and conjecture. This curiosity led to the birth of new ideas, a reality that was no longer tied to the physical world. Early humans began to develop explanations for what they could not see or understand. Spirits, gods, and forces of nature became personifications of the unknown. Fire, lightning, and stars were attributed to forces beyond human control. Through mythology and beliefs, they created a wider reality that filled the gaps left by their sensory limitations. This cultural development marked a turning point in human thinking. Humanity's journey, which began with a simple need to survive, has now evolved into something much more complex. In one of the earliest philosophical explorations of reality, Plato presents this allegory of the cave. In this mental experiment, prisoners have been confined in a cave all their lives, seeing nothing but shadows projected on the wall in front of them. These shadows are all they know about. They mistake these flickering figures for reality itself. For them, the shadows are the only truth that they can perceive. But what if they broke free of their chains and turned around? What would they see? Plato's allegory suggests that human perception is often limited. What we perceive as reality may only be a shadow of a deeper, truer existence. The path to understanding true reality, Plato argued, begins with questioning the world as we perceive it. Plato's allegory is not just a philosophical exercise. It is a profound commentary on the limits of human perception. We may think we see the whole picture, but we're often limited by the limits of our senses and our experience. Reality can thus extend far beyond what we can directly observe. In the physical world, our understanding of reality underwent a significant change with the discovery of space-time. In the early 20th century, Albert Einstein shattered the age-old foundation of classical physics by showing that space and time are not separate entities, as previously thought, but are instead interwoven into a single four-dimensional fabric, space-time. According to Einstein's general theory of relativity, massive objects warp this fabric, creating what we experience as gravity. Planets revolve around the sun, not because they're pulled by some invisible force, but because the sun warps space-time around itself, creating a curved path for them. This revolutionary concept has completely changed our view of reality on a cosmic scale. Time, too, is no longer absolute. In Einstein's universe, time can be stretched or compressed, depending on the speed at which an object is moving, or its proximity to a more massive object. This idea, time dilation, means that time itself is relative, which changes our perception of how reality unfolds. The scientific method has for centuries allowed us to peel back the layers of this reality. Classical mechanics, developed by Newton, gave us the tools to understand the motion of objects by accurately predicting their trajectories. But as we began to delve deeper into the nature of the universe, discoveries, especially in quantum mechanics and relativity theory, showed us that reality operates in ways that had previously defied common sense. The search for the basic building blocks of reality began thousands of years ago. Back in the 5th century BC, the Greek philosopher Democritus suggested that everything in the universe consists of tiny, indivisible particles, atoms. These atoms, he argued, are the fundamental building blocks of all matter. This idea persisted for centuries until modern atomic theory took shape in the 19th century. Scientists such as John Dalton began to provide empirical evidence that all matter was indeed made up of atoms. These tiny particles, invisible to the naked eye, joined together in various ways to form everything from the air we breathe to the stars in the sky. Atoms were long thought to be the most fundamental, indivisible units of the physical world. But as our understanding deepened, we discovered that the atom itself could be broken down into even smaller particles. In the early 20th century, the discovery of subatomic particles, protons, neutrons, and electrons, showed that atoms were not indivisible after all. These subatomic components opened the door to a whole new field of physics, quantum mechanics. Quantum mechanics offered a radically different view of reality. At the atomic level, particles behave in ways that defy the rules of classical physics. Electrons don't just revolve around the nucleus in neat, predictable trajectories. Instead, they exist as probabilities. Their location not fixed until they are observed. This strange behavior introduces the concept of superposition. Particles can exist in multiple states simultaneously until they're measured. At this level, the very nature of reality itself becomes uncertain. Classical physics taught us that the universe works like a precise machine with predictable cause and effect relationships. But quantum mechanics has shown that reality, at its core, is governed by probabilities. This new understanding challenged the notion of a solid, deterministic universe and replaced it with one in which randomness and uncertainty reign. So, as our understanding of the atom deepened, it became clear that even protons and neutrons, the components of the atomic nucleus, are not the most fundamental units of matter. Within these particles, scientists have discovered quarks, elementary particles that come together in certain combinations to form protons and neutrons. Alongside them were particles called gluons, which are responsible for binding quarks together, acting as mediators of the strong force, the fundamental interaction that holds the atomic nucleus together. Quarks, however, are unlike anything else in the world of physics. They cannot exist individually, only in combinations, bound together by a strong force. This force is so powerful that trying to separate quarks results in more quarks. It is a strange and complex system that continues to challenge our understanding of the fundamental structure of matter. Subatomic physics, and especially the study of quarks and gluons, has pushed the boundaries of our knowledge, making it even more uncharted. Although the standard model of particle physics successfully explains many particles and forces in the universe, deeper questions remain. How do these particles interact at the most fundamental level? What are the true building blocks of reality? One of the boldest theories in the search for answers to these questions is string theory. This revolutionary idea suggests that the fundamental particles we observe, quarks, electrons, and others, are not point particles at all, but tiny one-dimensional strings. These strings vibrate at different frequencies, and their vibrations give rise to the different types of particles we observe. String theory is not limited to the redefinition of particles. It suggests that these strings exist not only in the familiar three dimensions of space and one dimension of time, but also in multiple dimensions, perhaps 10 or 11. These additional dimensions are beyond our immediate perception. They're coiled so tightly that they remain hidden from view. If string theory is correct, then reality may be far more intricate than we ever imagined, and extend into realms we've yet to observe. And this brings us to Copenhagen interpretation, one of the most famous philosophical foundations for understanding quantum mechanics. Proposed by physicist Niels Bohr, this interpretation is based on the idea that quantum particles do not possess certain properties until they are measured. Before observation, they exist only as probabilities. It's the act of measurement, the interaction with a conscious observer, that gives rise to reality. In other words, until you observe a particle, its state is fundamentally undefined, neither here nor there. However, not all physicists are satisfied with the Copenhagen interpretation. Some prefer the more radical, many worlds theory, first proposed by Hugh Everett. According to this interpretation, every time a quantum event occurs, every time a particle's wave function collapses, the universe splits. In one universe, the particle follows one path. In another, it follows a different path. Instead of converging to one outcome, all possible outcomes occur, but in different branching universes. These parallel worlds exist simultaneously, each representing a different version of reality. The theory of multiple worlds provides an alternative to the idea that observation leads to a so-called collapse of reality. Instead, it argues that all possible realities exist, but we're only aware of the one we live in. This is a striking concept. It expands the imagination and makes us think that reality is much more layered than we see in everyday life. Whether we adhere to the Copenhagen interpretation, the many worlds theory, or some other explanation, one thing is clear. At the quantum level, the rules of reality are not at all what they seem. Despite its elegance, however, string theory remains largely unproven. The theory operates on such small scales that modern technology can't yet test its predictions. Even with all of our advances in subatomic physics, there is still much we do not know. Quantum mechanics and general relativity, the two pillars of modern physics, are still incompatible with each other, especially when it comes to explaining gravity on the smallest scales. While the Standard Model describes known particles and forces, it fails to account for dark matter, dark energy, and a complete explanation of gravity, suggesting that there's much more to reality than we can perceive or measure. So the question arises, where are you now? Not in the physical sense or location, but in the sense of experience. Your consciousness is the lens through which reality is perceived. But what exactly is consciousness? Is it simply the result of electrical signals and chemical reactions in the brain? Or is it something more? A fundamental part of reality itself? For much of modern science, consciousness has been understood as a byproduct of the brain, an emergent property arising from the complexity of neurological processes. Billions of neurons working in concert to form complex networks generate everything we feel, think, and perceive. From this perspective, consciousness is simply what happens when the brain reaches a certain level of complexity. But this explanation does not fully solve the mystery. The hard problem of consciousness is how philosopher David Chambers put it, is the question of how and why subjective experience, a sense of awareness, arises from purely physical processes. Why should a particular arrangement of neurons produce a vivid inner world of visual images, sounds, emotions, and thoughts? The gap between the physical workings of the brain and the richness of conscious experience remains one of the most confusing questions in science and philosophy. Some argue that consciousness is not just a byproduct of matter, but something much more fundamental. Some theories suggest that consciousness may be woven into the very fabric of reality, much like space and time. This idea, known as panpsychism, asserts that consciousness is not limited to humans or animals, but is a basic property of all matter, pervading the universe to some degree. So, if consciousness is fundamental, it could mean that the universe itself has consciousness to some extent. This shifts the question from how does the brain produce consciousness to how does consciousness manifest itself through matter? This in turn suggests that the distinction between mind and matter may be artificial, that consciousness and the material world are deeply interconnected. Other theories offer a more traditional approach. Consciousness is an emergent property. According to this view, the complexity of the brain creates consciousness in the same way that water emerges from individual hydrogen and oxygen molecules. In this view, consciousness is completely dependent on the physical structure of the brain. When the brain ceases to function, consciousness disappears. But this explanation still leaves unanswered the fundamental riddle of subjective experience. Philosophers and scientists have debated the true nature of consciousness for centuries. Is it reducible to material processes? Or is it something more? Something that perhaps eludes our current understanding of physics and biology? If consciousness plays a role in shaping what we perceive as reality, could it be that our subjective experience is not just a reflection of reality, but part of its very foundation? Ultimately, the nature of consciousness remains one of the greatest mysteries. What is it about consciousness that distinguishes it from everything else in the universe? Is consciousness a window into a deeper level of reality, or just a byproduct of complex physical systems? The question of where you are, where consciousness fits into the grand plot of existence, remains an open question. The more we learn about the brain and the universe, the clearer it becomes that reality may be far more intricate than we can currently comprehend. Perhaps one day, discoveries will show that consciousness is not just something happening inside reality, but a fundamental key to understanding reality itself. Humanity stands on the threshold of a new era, an era defined not only by exploration, but also by the bold dream of colonization. For decades, our gaze has been fixed on the familiar: the Moon, our celestial neighbor, and Mars, the red beacon in our night sky. These worlds, once the subject of science fiction, now beckon us with the promise of new frontiers. But beyond these well-trodden paths lies a world shrouded in mystery, a world that's changing our understanding of what it means to be a moon. This is Titan, Saturn's largest satellite. Titan is a world covered with a dense atmosphere, which is rare for a moon. It's a place where rivers and lakes flow not with water, but with liquid methane and ethane. Here, the sky is raining gasoline. And the cold is beyond anything that can be experienced on Earth. Yet, in this alien landscape lurks the potential for something extraordinary. Could Titan, a world so unlike our own, hold the key to our future in space? Could this distant moon hold the secrets to not only surviving, but thriving beyond our home planet?
It's one small step for man, one giant leap for mankind.
As we turn the pages of our history of space exploration, the Moon and Mars become beacons of human ambition. The Moon, our nearest celestial neighbor, has always been a constant companion in our night sky, a symbol of our desire to leave the confines of the planet. Mars, in turn, with its striking resemblance to Earth, fuels our dreams of finding a new home in space. Nevertheless, the Moon, despite its proximity, presents serious problems. Its surface is a barren wasteland, devoid of atmosphere and offering no protection from the harshness of space. The lunar environment is a vacuum, exposing astronauts to extreme temperatures and cosmic radiation. No atmosphere means no air to breathe, no wind to carry sound, and no sky to protect against the relentless barrage of solar and cosmic rays. Mars, though more Earth-like, is not without its own problems. Its thin atmosphere, consisting mostly of carbon dioxide, offers little protection from solar and cosmic radiation. The Martian environment is harsh and merciless, and temperatures at the poles can drop to minus 257 degrees Fahrenheit. The lack of a global magnetic field exposes the surface to the full force of the solar wind and cosmic rays. In contrast, Titan, Saturn's largest satellite, presents a very different environment. Shrouded in a dense atmosphere, Titan offers a natural barrier against the dangers of cosmic radiation. This atmosphere, richer in nitrogen than even the Earth's atmosphere, is the key to protecting future colonists from cosmic rays that mercilessly bombard less protected worlds such as the Moon and Mars. Titan's atmosphere isn't just a shield, it's a gateway to opportunity. Unlike the Moon and Mars, the air pressure on Titan's surface is 1.5 times higher than on Earth, creating a surprisingly familiar pressure environment for human explorers. This dense atmosphere opens up new possibilities for exploration and colonization, possibilities that are beyond the reach of our more trivial space goals. As we rethink our goals for space colonization, Titan becomes a compelling alternative, a world in which the atmospheric and radiation problems that limit our ambitions on the Moon and Mars become its strengths. Titan invites us to envision a future in which humanity can thrive under the protective embrace of an alien sky. A future in which the mysteries of this distant moon become stepping stones to our expansion into space. As we mentioned earlier, Titan, a moon of many mysteries, orbits around Saturn. Discovered in 1655 by Dutch astronomer Christian Huygens, Titan has captivated the imagination of scientists and dreamers ever since. This world is both similar to and in stark contrast to our Earth. Titan's environment is unlike anything else we've encountered in our solar system. It's the only known moon with a dense atmosphere, and the second largest moon in our solar system after Ganymede, a satellite of Jupiter. But it's not just the size that makes Titan stand out, it's the rich composition of its atmosphere and surface that really sets it apart. This moon is surrounded by a thick, nitrogen-rich atmosphere, similar in composition to Earth's, but far denser and more extensive. It's permeated with organic molecules, creating a kind of hazy orange glow that obscures the surface of the satellite from view. It's this nitrogen-dominated atmosphere that provides protection from solar radiation, which contrasts sharply with the barren sky of the Moon and Mars. Beneath this alien sky lies a landscape at once familiar and utterly alien. Titan's surface is formed by rivers and lakes, but they're not bodies of water as we know them. Instead, they're filled with liquid methane and ethane, flowing through channels carved into the Moon's icy crust. These hydrocarbon seas are a true marvel, a testament to the diversity of the universe's chemistry. The presence of these surface fluids is a key characteristic that distinguishes Titan from other celestial bodies. On Earth, the water cycle shapes climate and geography. On Titan, a similar cycle occurs, but the role of water is played by methane and ethane. This hydrocarbon cycle, with methane rain and ethane lakes, creates a dynamic environment that may provide clues to understanding the complexity of planetary atmospheres. So, by breaking the limits of our standard perception, we're slowly uncovering exactly what makes a planet or moon habitable. Its nitrogen-rich atmosphere and surface fluids open the door to new possibilities. Let's find out what they are. So the Moon's nitrogen-rich atmosphere provides a natural barrier against cosmic radiation, a major challenge for space colonization. Why do we pay so much attention to solar radiation? Well, the answer is simple, yet profoundly important. Solar radiation is a ruthless destroyer of living cells. It doesn't just affect microscopic life forms, it directly affects us as human beings. Unshielded exposure to solar radiation can cause severe cellular damage, destroying the very fabric of our biological existence. In space, spreading uncontrollably, this radiation poses one of the greatest threats to the survival and health of astronauts. On Earth, it's the atmosphere and magnetic field that protect us. On Titan, it's the dense nitrogen atmosphere that provides vital protection, making it a safer haven for future human colonists than the barren landscapes of the Moon or Mars. Beneath this protective dome is a world of liquid methane and ethane. These hydrocarbon lakes and rivers stand in stark contrast to the bodies of water we know on Earth, yet they offer intriguing possibilities. Imagine a world where boats sail on methane seas, where the familiar concept of the liquid cycle takes on a whole new form. The presence of these surface fluids is not just a curiosity, it's a resource. Methane and ethane have the potential to be used as fuel, providing energy for future colonies. This abundance of hydrocarbons makes Titan an attractive target for colonization, offering a solution to one of the biggest problems of space habitation: sustainable energy sources. But Titan's gifts don't end there. Beneath its icy surface lies another treasure: water ice. The very water so essential to human life is abundant on the satellite, trapped in its frozen crust. The presence of water ice, along with hydrocarbons, makes this moon a repository of vital resources, setting the stage for a self-sustaining human presence away from Earth. Titan, a world of incalculable potential, also presents enormous challenges. Severe cold, during which temperatures drop to minus 356 degrees Fahrenheit, creates an environment unsuitable for human life as we know it. In turn, methane rain, a phenomenon unique to this moon, adds another layer of complexity to the survival equation. To overcome these challenges, we must turn to the pinnacle of human ingenuity and technology. Colonizing Titan will require not just adaptation, but a complete rethinking of human habitation in extreme conditions. Imagine dwellings designed to withstand low temperatures, insulated with materials yet to be invented, and harnessing the power of Titan's own resources to provide warmth and comfort. These habitats could be equipped with systems to convert atmospheric methane into heat, turning the problem itself into a resource for solving it. But survival is more than just keeping warm. Methane rain, while an obstacle, could turn into an advantage. Advanced collection and filtration systems could recycle methane not only as an energy source, but also as a raw material for essential commodities. Now, let's imagine a human colony on Titan. Imagine domed cities, their architecture a blend of science and art, designed to harmonize with Titan's unique environment. These structures, resistant to cold and methane rains, would be interconnected, forming a network, demonstrating human resilience in the face of alien conditions. Inside these domes, life thrives. Hydroponic gardens provide food, recycling systems conserve resources, and public areas foster a sense of community. It's a place where humanity has not just survived, but flourished, adapting decisively to Titan's challenges. Colonizing Titan is not just a distant dream. It's a future that beckons us to take up the challenge. With each technological breakthrough, with each bold leap of imagination, we come closer to making this alien world a new home for humanity. Watching the thriving human colony on Titan, it becomes clear that this moon is more than just a new home for humanity. It's a center of economic and scientific opportunity. The unique environment and abundant resources offer unprecedented prospects for both. The economic benefits of colonizing Titan are rooted in its vast hydrocarbon reserves. Key components of Titan's lakes and atmosphere are not only potential sources of energy, but also valuable raw materials for chemical synthesis. The ability to harness these resources could turn Titan into an economic center, meeting both the colony's needs and potentially supplying materials for interplanetary trade. Scientifically, Titan is a gold mine. Its complex atmosphere and surface chemistry offer unique research opportunities that offer insights into organic chemistry and astrobiology. Studying Titan's methane cycle and its prebiotic chemistry could unlock the secrets of the origin of life, not only on Earth, but potentially throughout the cosmos. Moreover, Titan's position in the solar system and its resources make it an ideal launching pad for future space exploration. Its low gravity and abundant fuel reserves could make it easier to launch spacecraft to distant destinations, making Titan a strategic outpost for exploring the outer solar system and beyond. However, with these opportunities come important ethical considerations. As we embark on the colonization of Titan, we must reflect on our responsibilities in interacting with the new world. Conservation of Titan's environment, respect for its unique characteristics, and thoughtful stewardship are paramount. We must approach Titan not as conquerors, but as custodians. How we relate to this world in the future will reflect our values and our ability to balance progress and responsibility. As we conclude our journey, let's reflect on the key points. A moon once shrouded in mystery has turned out to be a world full of potential. We explored the protective properties of Titan's nitrogen-rich atmosphere, a natural shield against the dangers of cosmic radiation. We traveled through alien landscapes where rivers and lakes of methane and ethane cut through icy terrain, offering resources that could secure our future in space. Our journey also took us to the potential of a vibrant human habitat, where ingenuity and resilience have turned challenges into opportunities. We saw how Titan's economy, driven by its abundant resources, can be a cornerstone of our interplanetary endeavors. As we ponder the future of humanity on Titan, we're reminded that colonization is not just about achieving technological perfection. It's a journey that forces us to grow, learn, and respect the universe we live in. So we leave you with a great question. What does this step mean for the future of humanity? How will our efforts on this distant moon affect our destiny in the vast, uncharted expanse of space? The solar system has served as a reliable bulwark for life. But one day, humanity will have to leave its native Earth to continue existing. In recent decades, scientists have been desperately looking into the dim depths of space in search of a haven for life. So far, none of the exoplanets we've found have refuted the hypothesis of the uniqueness of life. But what if we're simply looking in the wrong place? Perhaps it's not the planets that hold all the answers, but their moons. In the mystical deep space, exomoons are unlike any other satellite in the solar system. The size of our Earth, these hidden giants have an amazing feature. Life can be found in their interior, many times more often than on ordinary exoplanets. Today, we'll dive into the mysterious, distant universe and try to discover why exomoons may someday change humanity. Let's go back to the very beginning of the history of exoplanet science. Since astronomy received a strong impetus only in the middle of the 20th century, scientists began to study the first exoplanets not so long ago. The first confirmed exoplanets were recorded in 1992. It was a group of Earth-mass planets orbiting the pulsar PSR B1257+12. Just 3 years later, scientists found the first planet orbiting the star 51 Pegasi, similar to our Sun. This was the birth of exoplanetary science, which is dedicated to the study of planetary systems outside our solar system, and, in addition, the search for places where human-like life could originate. Other exoplanets available in our visible universe didn't have to wait long either. In the following years, astronomers found several more exoplanets, until in 2009, the Kepler Space Telescope was sent to explore outer space. In just 5 years of operation, it was able to confirm about 715 exoplanets, with a size and conditions similar to Earth's. As of now, we already know about more than 5,500 planets outside the solar system, and the recently sent James Webb Telescope will likely to be able to show us even more distant planets. Further, in 2013, scientists were able to determine the planet's color for the first time, and a year later, they were able to record the magnetic field, and later, volcanic activity. Finally, in 2018, astronomers made a new, potentially breakthrough discovery. For the first time, a possible exomoon was recorded near the planet Kepler 1625b. While this may not seem like such an incredible discovery at first glance, exomoons open a new chapter in modern astronomy, not only as novel, hitherto unexplored space objects, but also as potential elements for supporting life on exoplanets and satellites themselves. Every year, knowledge about distant, dim exoplanets deepens, bringing scientists closer to a complete picture of the history of the entire universe. But how did the scientists manage to confirm so many planets in such a short time when it's impossible to take a photo of each one? Only 69 planets were found with images. The most popular method is the transit method, which you may already know. When an exoplanet passes by its central star, the same star becomes slightly dimmer, which reveals the presence of an object orbiting it. Although this method doesn't allow us to directly observe the planet, and may turn out to be just a glitch, it is currently the most effective of all. Exoplanet exploration plays a crucial role in all of astronomy and the future of all of humanity. Exomoons, as a new chapter in exoplanet science, may have great potential for the search for extraterrestrial life. However, despite this, exosatellites are of not much interest to current research. The main problem associated with the search for these exoplanets is their elusiveness to telescope radar. Although no scientists deny that some exoplanets may have satellites, it's an extremely difficult and, to some extent, possible task for our current technologies to investigate them. The transit method, or more precisely, the method of studying the shift in the spectrum of stars, can confirm an exoplanet. But a satellite orbiting it? Almost under no circumstances, unless, for example, the spacecraft is in the closest possible proximity to the object of observation due to a completely insignificant change in the brightness of the star. Thus, even the very first exomoon found by Kepler and the ones discovered later near the planets Kepler 1708b and Kepler 1513b are still not perceived as full-fledged proof of their existence, and therefore there is a possibility that it could be just some kind of technical error during the observation, which is not so far from the truth, since further observations did not yield any encouraging results. However, as in the case of the giant planet satellite Kepler 1625b, an exomoon can be seen if it is large enough. So far, the first hypothetical exomoon could be the size of the Earth and have a strange tilted orbit like Neptune's moon Triton. Such a huge size of a possible moon may become one of the most important elements in the further search for other moons. Thus, more than 20 exomoon candidates are currently known. All of them are gigantic. Probably at least for Kepler 1625b, it's the star around which it orbits. It is a red giant. This dying star can heat the moon's atmosphere, increasing its effective diameter and allowing scientists to detect satellites more often. However, perhaps right now, exomoons are not of too much scientific importance for scientists to invest a lot of resources in developing technologies to find them. At this stage of our science, exomoons don't seem to be a higher priority than other space objects, such as exoplanets. The satellites of distant planets are too complex to study and have a very high chance of a false positive result. Therefore, it may take months or even years of observation and analysis to confirm one satellite, when it seems more rational to spend this resource on exploring a planet with potential support for life, including human life. Of course, it is possible that exomoons may hide life in their interior, but alternatives in the form of rocky exoplanets like Earth are still of much higher importance in scientific circles. But we're going to focus on the exomoons themselves and try to investigate them. Is there any need to study these mysterious and hidden moons at all? In fact, these moons contain a lot of information for our complete understanding of the structure of the universe. But this will only be possible in the future, albeit not in the near future. The first thing that draws scientists' attention to even just candidates for exomoons is their size. The largest moon in the solar system, Ganymede, orbiting Jupiter, has a diameter of 3,273 miles, or 5,268 kilometers. But recorded exomoons can reach the size of the Earth, or even Neptune. Therefore, since such moons are even difficult to distinguish among exoplanets, it's incredibly exciting to imagine what moons might look like and what activity they exhibit. It's possible that some large exomoons have many of the features of planets, and that their study could overturn everything we know about satellites. Their similarities to other exoplanets, such as their likely geologic activity, bring us to the next important point for careful study in the future. and that is the support of life. We know that several moons of the solar system, such as Enceladus or Europa, despite their low surface temperatures and small size, could, hypothetically, be a haven for living organisms due to the presence of global oceans. However, what about the much more massive moons, which not only can support a dense atmosphere, but also have more access to building chemicals, both from the inside and outside? According to a study by the University of Washington, exomoons have more potential to support life than even exoplanets. They also have a habitable zone, although it's slightly different. But the main argument for exomoons as one of the most intriguing places for life to exist is the availability of several heat sources for them. The first source is the star itself, and the second is their planet. The moons are heated by the gravitational pull of the planet, which keeps the probable water in the interior of the moon in a liquid state. Moreover, heating from an exoplanet can stimulate geological activity, such as volcanic eruptions, creating enough gas inside the moon to maintain an atmosphere for a long time, and also bringing various crucial chemical elements to the surface. So exomoons are not as simple as they may seem. Perhaps the difficulty of finding them will be rewarded with a potential breakthrough in science. Finally, exomoons may become the necessary tool to study the formation of our universe. Thus, the analysis of exomoons near different stars and planets can reveal to scientists how space objects are formed, what factors are responsible for supporting life, and what the history of other planetary systems is in general. In particular, comparing the moons of the solar system with those of distant systems can give scientists an understanding of the specifics and conditions of their development, as well as an approximate value of the abundance of systems where complex intelligent life has developed. The Earth, hypothetically, may be almost the only planet on which life could have formed, at least in the visible universe. And any clues on exomoons with potentially higher chances of supporting living organisms can confirm or deny this. However, for now, deep exploration of exomoons is only a matter of the future. On the other hand, the James Webb Space Telescope mission will continue for several more years, so perhaps the hope of finding an exomoon for the first time in this decade is not going away. Nevertheless, since the search for exomoons is an extremely difficult and almost impossible task for our current technologies, exomoons are likely to become one of the drivers of technological progress. As we know, the transit method or gravitational lensing will not help to look for microsigns of the presence of exomoons, so this factor is already challenging scientists to modify or even create new technologies to capture such subtle objects. But this is a task for the near future. In the long term, both intriguing moons and exoplanets will require much more thorough analysis, including using images and samples of the atmosphere or even soils. So, if interesting candidates where extraterrestrial life exists are ever found, then comprehensive space missions are likely to follow, advancing human knowledge of the research focus. The only step we have left to take is to find such an exoplanet or exomoon. In 2026, the European Space Agency plans to send the Plato mission, which will continuously look at several areas in outer space to capture transiting objects. The mission will last for 6 years and may be the one to make this expected discovery. However, the benefits of exomoon search and exploration do not end with a technological breakthrough. Exomoons are very valuable natural laboratories located near various planets and stars. Analyzing the impact of these bodies on the moons will not only deepen what's known about the formation of planets, but also demonstrate to scientists the variety of conditions under which life can develop. For example, traces of bio or even techno-signatures created by civilizations on various moons can provide a clearer picture of the signs for the development of intelligent life, thus building more prioritized paths for future missions to the most likely planets or moons for aliens to live on. But for now, we can only wait for the moment when we find the first exomoon and begin a long but life-changing scientific and technological ascent. Exomoons, despite their invisibility and skeptical insignificance, may one day critically change everything known to the entire human race about our vast universe. Even a small observation can eventually become the main driver for revolutionary discoveries. Continued research will reveal more and more answers, and only by pursuing this knowledge will the cumbersome, mysterious cosmos one day become less confusing to us. But in the face of the vast universe, we must never lose our enthusiasm for learning, no matter how difficult and distant our desired outcome. Amidst the peace and tranquility of the celestial bodies of the solar system, there is one object that greatly disturbs the peace of the rest: the Moon, Io. Unlike any other orbiting the mighty Jupiter, shrouded in mystery, Io is a world of fire and fury, a stark contrast to the icy moons and calm planets that share its cosmic neighborhood. This mysterious moon, the most volcanic body in our solar system, is a testament to the dynamic forces at work in the cosmos. Its surface, riddled with hundreds of active volcanoes, tells the story of the relentlessly complex gravitational pull of Jupiter and other moons. Meet Juno, NASA's intrepid explorer, on a journey to this fiery world. Its mission is to unravel the mysteries of Io, capture its fiery essence, and uncover the secrets that have long lurked beneath its tumultuous surface. As Juno makes its closest approach in 2 decades, we stand on the threshold of new discoveries and are ready to unravel the mysteries of this volcanic moon. What will Juno tell us about Io's turbulent volcanoes? How does the turbulent nature of this moon affect giant Jupiter and its other moons? And what can Io tell us about the forces that shape our solar system? Let's find out. Discovering new space vistas, Juno, a spacecraft made not only of metal and circuitry but also of ambition and curiosity, is embarking on a journey that hasn't been taken in more than 2 decades. For the first time in 20 years, a spacecraft dares to come so close to Io that we can come face to face with a world of extreme volcanic activity. Juno's close approach is not just a routine flyby, but a bold dive into the unknown. The spacecraft, equipped with state-of-the-art instruments, is designed to withstand the harsh radiation environment of Jupiter and its moons. As it approaches the rough surface of Io at a distance of 930 miles, Juno's sensors come to life, taking high-resolution images and collecting valuable data. In late 2023, the probe made its closest flyby of Io, taking some incredible images in the process. In them, Jupiter's moon appears to glisten with sulfuric hues, and its surface is speckled with spots created by the ongoing volcanic activity that rages on it. By combining data from this flyby with our previous observations, the Juno science team is studying how Io's volcanoes vary, says astronomer Scott Bolton of the Southwest Research Institute. We are looking for how often they erupt, how bright and how hot they are, how the shape of the lava flow changes, and how Io's activity is connected to the flow of charged particles in Jupiter's magnetosphere. The heart of this mission lies in the technological prowess that Juno possesses. The spacecraft's JunoCam continues to take spectacular images despite the challenges of Jupiter's intense radiation. The Stellar Reference Unit's Stellar Navigation Camera is also a scientific instrument, providing the highest resolution images of Io's surface to date. On Earth, scientists are studying the data coming from Juno. Each byte of data is a piece of the puzzle, revealing new information about the volcanic nature of Io. Analyzing this is a window into our solar system's past, present, and future. So, late last year, NASA's Juno probe took the highest resolution images of this moon to date. Among these images, one that stands out is one taken on December 30th, which vividly depicts the volcanic nature of Io. This image, enhanced to emphasize details, shows a volcanic plume erupting from Io's surface, with plumes reaching more than 60 miles, given that the moon's diameter is about 2,200 miles. As Juno continues its journey around Jupiter, each orbit brings new opportunities, new challenges, and new discoveries. Among the planet's other 95 moons, Io stands out not only for its proximity to Jupiter, but also for the dramatic geologic activity that this proximity provokes. The volcanic nature of the moon is a direct consequence of Jupiter's enormous gravitational forces. Io is not a huge moon. It's only slightly larger than the one orbiting our planet. However, as the largest planet in our solar system, Jupiter has tremendous gravity. This enormous force stretches and squeezes Io, creating what is known as tidal heating. The satellite's orbit itself is not a perfect circle, resembling more of an ellipse, so the moon experiences varying degrees of gravitational pull from Jupiter. As it approaches Jupiter, the planet's gravity stretches Io, and as it moves away, it compresses it. This constant stretching creates tremendous internal heat within Io, leading to its intense volcanic activity. This JunoCam image captures a plume of material ejected from the unseen volcanic Prometheus. Indicated by the red arrow, the plume is just visible in the darkness below the terminator, the line dividing day and night. The image was taken by spacecraft on October 15, 2023. Tidal heating is so intense that it turns Io's interior into a bubbling cauldron of molten rock. This heat leads to the volcanic activity that defines Io's landscape. Hundreds of volcanoes dot its surface, some of them spewing lava fountains up to hundreds of kilometers high. There are about 400 active volcanoes on Io, about 150 of which are erupting at any given time. But Jupiter is not the only player in this gravitational confrontation. The other Galilean moons, Europa, Ganymede, and Callisto, also exert their influence on Io. Their gravitational attraction helps to maintain Io's elliptical orbit, thus playing a crucial role in the tidal heating process. This complex gravitational interaction is a perfect example of how celestial mechanics determine the fate of a moon. The tidal forces of Jupiter and its moons don't just heat Io, they create a world in which geologic activity is the norm, not the exception. Io, a moon shrouded in fire and brimstone, plays a key role in the grand theater of Jupiter's system. Its incessant volcanic activity not only shapes the landscape, but also significantly affects the very nature of Jupiter's magnetosphere. As we mentioned earlier, the volcanoes on this satellite are the most active in the solar system. In doing so, they spew huge amounts of sulfur dioxide, or SO2, into space. This outgassing, a direct result of intense internal heating, contributes to an atmosphere rich in sulfur compounds. But Io's influence extends far beyond its own atmosphere. As Io rotates within Jupiter's massive magnetosphere, sulfur dioxide and other volcanic gases ionize, becoming charged particles. These particles become trapped in Jupiter's magnetic field, forming a plasma torus along Io's orbit. This torus, a glowing ring of ionized particles, is a direct manifestation of the moon's volcanic power. The plasma torus is not a static feature. It changes in response to Io's volcanic activity. The ejection of material from volcanoes feeds the torus, affecting its density and composition. This complex interaction between Io's volcanism and the plasma torus illustrates the interconnectedness of Jupiter's system. It's also thought to be responsible for powerful, permanent auroras at the planet's poles. Volcanic emissions, once in the atmosphere, escape into space. Here they undergo rapid reneutralization, a process that ejects these particles at high velocity in a plane perpendicular to the local magnetic field. This phenomenon continues to the formation of extended sodium nebulae, adding another layer to the complex environment around Jupiter. Observational studies have been crucial in shedding light on these interactions. For many years, telescopes, like TRAPPIST, have followed the variability of Io's sodium cloud. These observations have shown that the physical properties of the sodium jets from Io are highly variable and, interestingly, do not always correlate directly with the global brightening of Jupiter's plasma torus or the extended sodium nebula. This study highlights the complexity of the surface-atmosphere-magnetosphere coupling in the Jupiter system. Current research aims to reveal the precise mechanisms by which Io's volcanoes supply material to the plasma torus, and how Io's sodium jet contributes to filling the plasma reservoirs of the magnetosphere. Thus, Io's relentless volcanic activity and its interaction with Jupiter's magnetic fields are not just isolated phenomena. They play a fundamental role in shaping the dynamics of Jupiter's magnetosphere, producing plasma structures and neutron clouds that are key to understanding the complexities of planetary magnetospheres. Ongoing research and observations allow us to separate the layers of these interactions, offering a deeper understanding of the workings of our solar system. As we look to the future of space exploration, the fiery moon Io appears as a beacon of mystery and potential. The next phase of Io exploration is poised to reveal secrets that have remained hidden beneath its stormy surface for centuries. Introducing the Jupiter Icy Moons Explorer mission, abbreviated as JUICE. JUICE aims to study Jupiter's icy moons, offering intriguing opportunities to further our understanding of Io. Although JUICE's primary focus is on Ganymede, Europa, and Callisto, its extensive suite of instruments can provide valuable insights into Io's dynamic environment. The interplanetary spacecraft was launched on April 14, 2023, from the Guiana Space Center in French Guiana by the European Space Agency. The spacecraft is expected to reach Jupiter in July 2031 after 4 gravity assists and an 8-year journey. As JUICE passes through the Jupiter system, its trajectory may provide opportunities to observe Io. These encounters may provide additional data on the satellite's volcanic activity and its effect on Jupiter's magnetosphere, complementing the conclusions drawn by missions directly targeting Io. Equipped with sophisticated instruments designed to study magnetic fields, plasma environment, and atmospheric composition, JUICE has the potential to indirectly expand our knowledge of Io. By studying Jupiter's magnetosphere and the interactions within it, JUICE can provide a broader context for the satellite's role in the entire Jupiter system. Another mission, Io Volcano Observer, or IVO, is a bold initiative that represents the next leap in our quest to understand this volcanic moon. IVO is a proposed mission designed to study Io's intense volcanic activity, its subsurface structures, and the complex processes that drive its geologic dynamism. IVO's mission is to enter orbit around Io and make multiple close flybys. Equipped with state-of-the-art instruments, IVO will map Io's volcanic heat flows, study lava composition, and probe the moon's internal structure. This mission aims to answer fundamental questions about the mechanisms of volcanism on Io and the role of tidal heating in its activity. One of the most interesting aspects of the IVO mission is exploring the bowels of the moon. What lies beneath its fiery facade? IVO seeks to shed light on this mystery by studying the moon's internal structure. Seismic measurements and magnetic field analysis may reveal the presence of subsurface magma chambers and provide insight into the moon's volcanic flow system. The potential for new discoveries about Io's volcanic mechanisms is enormous. IVO observations could revolutionize our understanding of volcanic processes, not only on Io, but throughout the solar system. By studying Io's unique volcanism, we'll be able to gain insight into the thermal evolution of planetary bodies and the role of tidal forces in shaping planetary geology. In the meantime, Juno continues to work, with many more observations planned, not only of Io, but also of the other Galilean moons, and, of course, Jupiter itself. The spacecraft will continue to operate until September 2025, or until it breaks down, whichever comes first. In the meantime, we'll look forward to more images taken by the next flyby. Our universe hides a mystery that's long captivated the human mind. A question that bridges the gap between the known and the unknown, the simple and the complex. Here on Earth, life thrives in a continuous movement of order and chaos. Every form of life is evidence of a hidden order, a pattern woven into the very fabric of existence, from the smallest microorganisms to the largest mammals. But what if the complexity of life, the very essence of our existence, could be explained not only through the lens of biology, but also through a mathematical framework? This is the territory of assembly theory, a groundbreaking concept that transcends traditional science. It's a journey into a world where math and biology converge to reveal the hidden architecture of life. Imagine a universe in which the secrets of life, from the simplest molecule to the most complex organism, are encoded in mathematical language and are waiting to be decoded, where the line between living and non-living is blurred, giving birth to new possibilities and new understanding. Let's explore how this revolutionary idea is changing our perception of life, evolution, and the cosmos itself. And maybe we can even get closer to answering the ultimate question: what is the true nature of life in the universe? Since the dawn of civilization, mathematics has been the language of the universe, a tool for deciphering the mysteries of nature. But how does this language of numbers and equations relate to understanding the very essence of life? At its core, assembly theory offers a simple but profound idea. The complexity of life can be measured and understood through a mathematical prism. Think of life as a jigsaw puzzle, where each piece represents a molecular building block. Assembly theory seeks to show how these pieces come together step by step to form the complex structures that define living organisms. Each step in this assembly process represents a leap of complexity, from simple atoms to complex proteins. The theory introduces the concept of the assembly index. The assembly index, the cornerstone of this theory, measures the number of steps required to build a biological structure. It's a numerical value that captures the essence of complexity by quantifying the immeasurable. But how does the standard model of physics fit into this? This standard model theory of physics describes the fundamental particles and forces that govern our universe. It seems completely separate from the complexities of biology. However, assembly theory bridges this gap. In the field of assembly theory, the standard model lays the foundation for understanding forces and interactions. It's a bridge between the microscopic world of quarks and leptons and the macroscopic world of living things. Another important element of the theory is the concept of studying dynamical systems, phase space. This is a mathematical concept used to describe all possible states of a system. In the context of assembly theory, phase space allows us to map the path of the assembly of life. From a single point representing the simplest form of life, phase space expands, branching out into almost infinite possibilities. Each pathway representing a different route that life can take. In this limitless mathematical landscape, the paths of evolution and its complexities unfold. This mathematical framework gives us a new perspective on the complexity of life. It's not just about the particles and forces described by the standard model, but how these elements combine and interact over time to create the diverse pattern of life we see around us. This is where the chaos of random molecular interactions gives way to the order of living structures. So let's ask ourselves this question: are the complexities of life simply the product of chance? Or is there a deeper cause? Let us consider two sharply contrasting concepts: complexity and entropy. Entropy, a measure of disorder and randomness, seems to be at odds with the complexity we observe in life. How do these opposing forces coexist in the natural world? It's here that assembly theory offers a revolutionary perspective. So, central to assembly theory is the assembly index, a revolutionary tool designed to measure the complexity of life. Think of it as a cosmic ruler measuring the steps required to assemble a biological structure from its simplest components. Imagine a single molecule as the starting point on this scale. As you move up the scale, each step represents a more complex assembly, from molecules to cells and beyond. The higher the index, the greater the complexity, and the less likely it is that the structure could have arisen by chance. Now let's delve into the interaction between entropy and complexity. Entropy, a concept rooted in thermodynamics, suggests that systems naturally tend toward disorder. However, life defies this tendency, evolving from simple origins to a variety of forms combined into the complex ordered structures we see today. How does assembly theory resolve this apparent contradiction? It suggests that life is inherently a process of overcoming entropy. Through the lens of the assembly index, we see the complexity of life is not a challenge to entropy, but a journey through it. Consider the early Earth, a primordial soup of simple molecules. Over millennia, driven by the laws of physics and chemistry, these molecules began to assemble into more complex structures. Each step along the way marked a victory over entropy, a step toward greater complexity in life. Rethinking evolution through assembly theory, we see it not as a mere biological process, but as a mathematical inevitability. The emergence and evolution of life became a story of increasing complexity, a story written in the language of mathematics. Let us now turn to a very trivial question, but one that shines in a new light. Are we alone? The search for extraterrestrial life has captivated our imagination for centuries. Now, thanks to assembly theory, we have a new tool in this cosmic quest. Assembly theory offers a unique approach to detecting alien life. It's not about scanning the sky for radio signals or analyzing light spectra for the presence of oxygen. Instead, it's about understanding the complexity of molecules and structures that may indicate life. Imagine scanning the atmosphere of a distant exoplanet or the surface of a moon in our solar system. Using assembly theory, we could analyze the molecular complexity of the samples in search of patterns that indicate the presence of life. The higher assembly index, the more likely it is that these molecules are the result of life rather than random processes. However, the road to discovering alien life is full of challenges and limitations. One of the biggest obstacles is our understanding of life itself. Our definition of life is based on what we know. Life on Earth. What if it doesn't meet our biochemical standards? Another problem is the vastness of space. The universe is vast, and our ability to explore it is limited by current technology. Even with the most sophisticated telescopes and probes, we can only analyze a tiny fraction of the cosmos. Moreover, assembly theory, while powerful, is still in its infancy. It's a new approach, and its application to the search for extraterrestrial life is uncharted territory. There are questions about its applicability and accuracy in different environments, especially those that are very different from terrestrial environments. Despite these problems, the potential of assembly theory in the search for alien life is enormous. It could redefine our understanding of life in the universe, opening new doors in astrobiology. So assembly theory offers a new way of looking at life, not just as a biological phenomenon, but as an emergent property of cosmic complexity. Imagine the early days of our planet, a world in motion, a crucible for the chemistry of life. Here in this chaotic environment, simple molecules began the journey of assembly, a process governed by the laws of physics and chemistry, but leading to something much deeper. Life, according to assembly theory, emerges when these molecular structures reach a level of complexity that allows them to store and reproduce information. This is where chemical memory, a crucial step in the evolution of life, comes into play. Chemical memory is the ability of certain molecular structures to retain structure. In other words, we can say this is the blueprint for life. In the world of assembly theory, This is where reproducibility becomes key. The ability to reproduce these patterns, to pass them on from generation to generation, is what drives the evolution of life. From the simplest RNA molecules in the primordial soup to the vast diversity of life we see today, each step in this evolutionary journey has been a step up the assembly index. Each increase in complexity represents a triumph over the entropy that governs the universe. But the story of the origin and evolution of life is not just a story of increasing complexity. It's also a story of resilience and adaptability. Life has found a way to thrive in the most extreme environments, from the depths of the ocean to the fringes of space. In the realm of scientific discovery, every new theory is scrutinized and debated. Assembly theory, a concept that promises to revolutionize our understanding of life and complexity, now stands at a crossroads, being questioned by critical voices such as Dr. Hector Zennel. The critique presented by Zennel raises fundamental questions about the future evolution of assembly theory. Covering an impressive 18,000 words, the article will require time and thought, taking approximately 1 to 2 hours of dedicated reading. This is not a cursory look at the topic, but a deep dive into the heart of the scientific debate. For those who are interested, we leave a link in the description to both articles, the study and the counter-arguments to it. Looking to the future, the role of assembly theory in scientific research remains uncertain. Will it be able to adapt and overcome these challenges, or will it remain a footnote in the history of science? Despite the disagreements, one thing is clear. The debates surrounding assembly theory have initiated a conversation about the nature of scientific discovery. They emphasize the need for transparency, rigor, and humility in pursuing knowledge. In the end, the impact of assembly theory on future research may not lie in its specific claims, but in the lessons it teaches us about the scientific process. As we explore the mysteries of life and the universe, such theories will come and go. But the quest for understanding, the quest to unlock the mysteries of our existence, will always remain at the center of the interest of scientific research. Imagine a time when the universe was a dark space, an era before the first stars lit up the heavens, a period known appropriately as the Dark Ages. It was a time when the cosmos lay shrouded in a cloak of mystery, filled with neutral hydrogen gas that hid the light, making the universe invisible to itself. But in this darkness, the seeds of change were sown. A pivotal event loomed on the horizon that would end the cosmic silence and usher in the epoch known as reionization. This transformative epoch remains one of the greatest mysteries since the Big Bang. The James Webb Space Telescope set out into the great unknown on a mission to unravel those very mysteries. Breaking through the veil of cosmic dawn, it offers us today a glimpse of an age when the universe awoke from darkness. What secrets are hidden in the light of the first galaxies? What forces ended the reign of the Dark Ages and heralded the beginning of reionization? And most importantly, how did these discoveries confirm or refute our theories of early expansion and the formation of cosmic structures? Join our journey to the very edge of space and time to trace the path of light back to its origins together. Just moments after the fiery birth of the universe in the Big Bang, the reality we know was unrecognizable. The newborn universe was a boiling cauldron of hot, dense plasma, a turbulent sea of subatomic particles colliding and combining in the extreme energies of the early cosmos. As the universe expanded, a cosmic interaction emerged in which matter and energy were linked by the rhythms of the nascent laws of physics. Expansion led to cooling, and within a few 100,000 years a transformation took place, Protons and electrons, once too energetic to bind, fused together to form the first neutral hydrogen atoms, casting a veil of darkness over the cosmos. This event marked the transition of the universe from a plasma state to a gas state, which led to the appearance of the cosmic microwave background, the first light of the universe, the faint afterglow of creation that can still be observed today. But along with this first light came the cosmic dark ages. Imagine a universe devoid of stars, where galaxies have not yet formed. A vast expanse of darkness pervaded only by the faint glow of the cosmic microwave background. Such was the universe during the Dark Ages, when light-emitting objects were absent and the all-pervasive neutral hydrogen gas formed a cosmic fog, absorbing any light that could ionize it. But in this darkness, the groundwork was laid for cosmic transformation. Dense clusters of gas began to gravitate toward each other, slowly thickening under the inexorable pull of gravity. These were the first steps toward forming the cosmic structures we see today, the precursors to the stars and galaxies that would eventually break through the darkness of the Dark Ages. As we plumb the depths of the origins of the universe, we are reminded of the profound transformations that shaped the cosmos. The Dark Ages, a period characterized by darkness and silence, were only a prelude to the events that followed. As the universe moved forward in time, leaving behind the Dark Ages, a monumental transformation was looming on the cosmic horizon. This was the age of reionization, a pivotal chapter in the grand narrative of our universe. Reionization refers to the process by which the neutral hydrogen gas that filled the early universe was ionized by the first light sources, effectively lifting the cosmic veil of darkness and allowing the universe to once again shine with light. This process is an important phenomenon in the history of our universe because it represents one of the few ways in which we can indirectly study the earliest stars and galaxies. Imagine the universe in a transitional period characterized by an abrupt transition from opacity to transparency. In it, the ubiquitous neutral hydrogen gas that once absorbed all ionizing light began to change. Tiny bubbles of ionized gas appeared as the first stars and galaxies formed, each becoming a cradle of light that pierced the surrounding darkness. These bubbles, at first few and isolated, began a journey of expansion and unification, marking the large-scale process of reionization that transformed the early universe. But what force was powerful enough to cause such a colossal change and gradually disperse this hydrogen fog? This question is at the heart of reionization, a mystery that astronomers and cosmologists have been piecing together clue by clue for decades. The prime suspects were the first luminous objects formed in the universe, the first stars and galaxies. These celestial formations, born from the gravitational collapse of dense regions in hydrogen gas, began to shine, their light making its way through the cosmic fog. According to the theory, the first stars were 30 to 300 times more massive than our Sun and millions of times brighter, burning for only a few million years before exploding as supernovae. Among these early stars, a special type known as Population 3 stars, massive and incredibly bright, shone with a fierce light. Originally thought to be composed solely of hydrogen and helium, these stars were the first to break the cosmic silence. Their intense ultraviolet light was capable of splitting hydrogen atoms into electrons and protons. In other words, ionizing them. However, the history of reionization is characterized by complexity and nuance. As the bubbles of ionized gas grew and merged, the role of these early stars has come into question. Were they alone responsible for this cosmic transformation? Or did other, more numerous and less luminous objects contribute to the process? The mystery deepened with the realization that the reionization process was not uniform, but discontinuous, with the ionization regions expanding at different rates and different directions. This diversity suggested a variety of sources, each of which made a unique contribution to the overall picture. This was the time when the universe underwent one of its most dramatic transformations, a period that allowed light to travel unimpeded across the vast expanse of space. This very moment was captured by the afterglow of the Big Bang, the cosmic microwave background, or CMB. The CMB serves as a relic snapshot of the universe in its infancy, giving us a glimpse of conditions at the dawn of cosmic reionization. After reionization in the cosmos, a fundamental question arises. What forces were powerful enough to end the cosmic dark ages and ignite the universe with light? The search for these driving forces leads us into the heart of the unknown. So as we discussed earlier, among the prime suspects are the elusive stars of Population 3. These theoretical giants, composed entirely of hydrogen and helium, are thought to be the first stars to crack the primordial darkness. Their intense ultraviolet radiation, capable of ionizing huge masses of hydrogen gas, makes them formidable candidates for reionization. However, their unstable nature and lack of direct observational evidence cast a shadow of mystery on their role. Another group of potential culprits are quasars, the extremely luminous nuclei of early galaxies, powered by supermassive black holes. These cosmic beacons, with their intense radiation, could ionize hydrogen gas over vast distances, carving out large ionized regions in the intergalactic medium. But like puzzle pieces that don't quite fit together, the distribution and number of quasars cast doubt on their ability to fully explain the observed ubiquitous reionization. However, the keen eye of the James Webb Telescope discovered that in the early universe, the cosmos is teeming with faint but unexpectedly numerous galaxies. These galaxies, less massive and less luminous than their later counterparts, may have played a more significant role in reionization than previously thought. Their abundance and the cumulative effect of ionizing photons emanating from them could have contributed significantly to the transformation of the cosmic landscape. If this were the case, instead of a few dominant sources, reionization could have been caused by a multitude of stars and galaxies, ending the Dark Ages. So what has JWST discovered? In the dense cosmic galaxy cluster Abell 2744, also known as the Pandora Cluster, a whole bunch of unremarkable dwarf galaxies have been uncovered. The luminosity of such galaxies is more than 100 times fainter than our Milky Way. Gravitational lensing played a crucial role in this study, acting as a cosmic magnifying glass. It allowed astronomers to observe and study extremely faint galaxies from the early universe that would otherwise have been invisible even to the very powerful Webb telescope. By warping the very fabric of space, the massive Pandora cluster amplified the light from distant galaxies, making them appear larger and brighter. In their study, thanks to this magnification effect, astronomers took and analyzed the spectra of 8 extremely dim galaxies. Such modest celestial formations, often overlooked in the cosmic timeline, have come to the fore, changing our understanding of the evolution of the early universe. This particular type of dwarf galaxy holds a surprising secret for its modest size. It emits huge amounts of ionizing radiation, 4 times larger than previously thought. Astronomers estimate that 50,000 sources of near-infrared light are present in the Webb image of the galaxy cluster, Abell 2744. To arrive at this conclusion, the team first combined data from ultra-deep JWST images with additional Hubble Space Telescope images of Abell 2744 to select extremely dim candidate galaxies in the epoch of reionization. The NIRSPEC near-infrared spectrograph was then used to study the emission characteristics from the distant objects. This discovery changes the paradigm of our perception of the initiators of cosmic reionization. For the first time, scientists have reliably measured the density of such faint galaxies and successfully confirmed that they are the most abundant population during the epoch of reionization. Their ubiquitous presence and significant ultraviolet emission indicate that they may have played a more important role in the end of the Dark Ages and the formation of the ionized landscape of the universe than previously thought. What makes dwarf galaxies particularly intriguing is their potential for uniform ionization. Unlike the large isolated bubbles created by more massive galaxies or quasars, the ionized regions around dwarf galaxies were likely smaller and more numerous, thus weaving together the complex network of light in the early universe. This complex structure of ionization, with countless small bubbles thickening with time, paints a picture of reionization that's more gradual and widespread than previously thought. A similar, unusual family of dwarf galaxies was actually discovered back in the last century, in the mid-1920s, the so-called green pea galaxies. However, it took scientists a long time to explain what they are, having unambiguously determined only in 2023. These galaxies got their name for their compact size and green glow in optical images. Green peas are characterized by an amazing ultraviolet luminosity, indicating active star formation and the enormous amount of ionizing radiation they emit. These galaxies, although small in size, play a colossal role in the history of cosmic reionization. The James Webb Space Telescope has shed new light on these enigmatic galaxies, revealing their architectural legacy on the canvas of cosmic evolution. Along with galaxies such as Haro 11, known for their intense ultraviolet emission, the green pea serves as a living laboratory, allowing us to observe ionization mechanisms in action and further confirming the conclusions of a previous study. Not the least of these studies is the theory of cosmic inflation, a sharp and rapid expansion that's believed to have occurred a fraction of a second after the Big Bang. According to this theory, the universe underwent an exponential growth spurt that smoothed out all the initial irregularities and led to the homogeneous and isotropic universe observed in the cosmic microwave background. Looking into the epoch of reionization, JWST offers a unique vantage point to study these underlying theories. By observing the earliest galaxies and their distribution, we will be able to find echoes of inflationary fluctuations and assess their consistency with predictions. The distribution, size, and number of ionized regions created by the first galaxies and stars during reionization provide insight into the density fluctuations in the early universe that were amplified by inflation. Density fluctuations in the universe are like having a large room full of people with a little more people and a little more emptiness. Imagine the room is filled with people standing equidistant from each other. This is similar to the early universe, which was mostly homogeneous. However, in some parts of the room, groups of people may stand a little closer, creating crowding, while other places may be a little more empty. In the universe, these crowded and empty spaces are areas where there is a little more or a little less matter, stars, galaxies, and gas, than average. Over time, gravity pulls more matter into the crowded places, making them even more crowded, forming galaxies and galaxy clusters, and leaving the emptier areas even emptier as gaps between the crowded places. This is how the structure of the universe, with all its galaxies and vast empty spaces, emerged from these initial small differences in the distribution of matter. According to this model, such masses such as the first stars and dwarf galaxies formed first, which gradually merged to form the grand galactic structures we see today. Such nuances lead us to reflect on the complexities of the expansion of the early universe and to ask critical questions in the future research. How do these observations of the reionization epoch fit with predictions of cosmic inflation? Do they support a model of hierarchical structure formation, or do they suggest refinements to our current understanding? A future Webb observing program called GLIMPSE will provide scientists with the deepest images of the sky in observational history, opening new windows into the earliest epochs of the universe. The study seeks to detect even fainter galaxies from the epoch of reionization. By targeting another galaxy cluster, Abell S1063, these observations will expand our cosmic census, potentially confirming the typicality of the dwarf galaxies observed in the current study and offering further insight into the large-scale distribution of galaxies in the early universe. This next step in the study could refine our understanding of the period known as Cosmic Dawn and the appearance of the first galaxies, shedding more light on the formation of the universe and its grand evolution. There is a hidden order in the void of space, a subtle force that controls the movements of the celestial bodies with an invisible hand. Far from the chaotic randomness one might expect in the vast cosmos, there is a mysterious harmony, a set of invisible rules that dictate the paths of planets, moons, and asteroids with remarkable precision. Consider for a moment that the giants of our solar system are not just isolated spheres of rock and gas, but participants in a grand gravitational party whose every move is influenced by the forces generated by their cosmic neighbors. Among the actors are Jupiter and its moons. Behind them also lies the asteroid belt, a vast ring of debris that holds voids of mysterious origin. These voids, devoid of the rocky features typically found in the rest of the belt, hint at an unseen participant silently shaping the structure of this cosmic phenomenon. Even distant Neptune and Pluto tell a tale of complex gravitational interaction, locked in such a precise rhythm that their paths never cross. These patterns and rhythms are constantly emerging in the vastness of space, hinting at the underlying order that governs the universe. Orbital resonance is the very concept behind this behavior. What forces act on this mechanism of behavior, both simple and bewilderingly complex at the same time? Let's find out. Behind the facade of the night sky, a complex network of forces operates to dictate the movements of celestial bodies. Gravity, the fundamental force that keeps our feet on Earth, extends far beyond our planet, creating the architecture of the cosmos on a grand scale. At the center of our solar system is the Sun, a colossal furnace of nuclear energy whose gravitational pull subordinates the motions of the planets around it. This gravitational interaction is not a one-way street. Each planet, in turn, exerts its own gravitational pull, creating a complex network of forces that affect their orbits. When two celestial bodies come close together, their gravitational fields interact, influencing each other as if playing a cosmic tug-of-war. This interaction can lead to subtle changes in their trajectories, an effect that's most pronounced in systems with closely rotating bodies, such as Jupiter and its Galilean moons. Consider the case of Jupiter, a giant of the solar system whose massive gravitational field holds a retinue of moons. Among them, the Galilean moons, Io, Europa, and Ganymede, exhibit a remarkable phenomenon known as mean motion resonance. This occurs when the periods of their orbits around Jupiter maintain a constant ratio, a delicate balance that prevents their trajectories from becoming chaotic, despite their close proximity. This gravitational interaction leads to a rhythmic alignment of the moons that repeats over time, ensuring their long-term stability. The forces at work do not simply pull the moons along their trajectories, but push them to positions that minimize potential disruptions to their orbits. Beyond the region of Jupiter and its moons, the gravitational interaction extends to the asteroid belt and beyond, where countless rocky bodies are influenced by the gravitational pull of nearby planets. This interaction can lead to gaps in the asteroid belt, regions devoid of asteroids formed by the resonant effects of Jupiter's gravity. Based on the above, we can conclude that gravity acts as a weaver in the cosmos, Its threads pull and shape the trajectories of celestial bodies, creating a harmonious order out of potential chaos. This gravitational influence, a fundamental aspect of the universe, provides the basis for the interaction of planets, moons, and stars. But is it as easy to understand as it is obvious? In the gravitational embrace of Jupiter, the largest planet in our solar system, there is an amazing example of cosmic harmony, the Laplace resonance. This unique gravitational relationship involves the three previously mentioned major moons of Jupiter, Io, Europa, and Ganymede. Each of these moons, a wondrous world, is involved in a synchronous orbital interaction that has intrigued scientists for centuries. Laplace resonance is characterized by the exact ratio of the orbital periods of these moons. For every 4 orbits that Io completes, Europa orbits twice, and Ganymede completes 1 orbit. Due to this gravitational pattern, the moons align at regular intervals in a pattern that repeats itself every 7 Earth days. Resonance is not just a curious phenomenon. It has profound implications for the moons themselves. Gravitational interactions, especially between Io and Europa, cause significant tidal heating on Io, which promotes volcanic activity. This energy dissipation also affects Europa, potentially contributing to the maintenance of its subsurface ocean. Laplace resonance provides a clear example of how celestial bodies, through mutual gravitational influence, can establish stable and predictable patterns that persist over centuries. But the story doesn't end with satellites alone. Saturn, the jewel of our solar system, is surrounded by a series of mysterious rings. These rings are made up of countless particles of ice and rock, from a speck of dust to a mountain-sized lump. And yet, among this continuously glowing belt are gaps, vast stretches of emptiness that baffle. What had to happen for them to occur? One of these discontinuities, the Cassini separation, is evidence of the forces of orbital resonance. It's not simply a lack of material, but a boundary created by the gravitational influence of Saturn's moon, Mimas. Mimas's role in creating this gap is a fascinating example of orbital resonance in action. Mimas, although small compared to the gas giant around which it orbits, exerts a significant periodic gravitational influence on the particles inside the rings. This effect is not random. It occurs at specific points in the orbits of the particles because their orbital periods are in resonance with the orbit of Mimas. For every 2 orbits that Mimas makes, the particles at the edge of the ring make 1, thus having a resonance in the ratio 2:1, which leads to repeated gravitational interactions at the same point of the particles' orbits. These repeated interactions have a cumulative effect and act like a cosmic broom, clearing the way and creating the Cassini separation. Particles that once occupied this space were either pushed into new orbits or stuck together to form larger bodies, leaving behind the void that marks the boundary between Saturn's A and B rings. This process is akin to nudging a seesaw at just the right moments. Each nudge adds a little more energy to the system, and in the case of the planet's rings, each gravitational push by Mimas moves the particles around, clearing a path in the rings. However, the influence of Mimas and orbital resonance is not limited to the Cassini separation. Similar resonances caused by Saturn's other moons shape the complex structures of the rings, creating a pattern of discontinuities and dense bands that make the planet's rings dynamic and ever-changing. Between the orbits of Mars and Jupiter lies the asteroid belt, a huge cluster of rocky remnants from the era of the formation of the solar system. However, this region is unevenly filled. There are distinct gaps known as Kirkwood gaps. These gaps are not the result of missing asteroids, but represent areas where Jupiter's gravitational influence has organized stellar clearing. Kirkwood gaps are named after Daniel Kirkwood, who observed in the 19th century that these gaps correspond to orbital resonances with Jupiter. In these resonances, the orbital period of the asteroid in the gap will have a simple ratio to Jupiter's orbital period, such as 1 to 2, 2 to 3, or 3 to 4. At such distances from the Sun, the asteroid's orbit will periodically align with Jupiter in a pattern that will be repeated at each orbit. Over time, these repeated alignments expose the asteroid to regular gravitational jolts from Jupiter, changing its orbit. When an asteroid falls into one of these resonance gaps, repeated gravitational jolts from Jupiter can increase the eccentricity of the asteroid's orbit, putting it on a more elliptical trajectory. This could cause the asteroid to move to a different orbit, leaving the resonance gap free. To visualize this phenomenon, imagine an asteroid approaching one of these resonant orbits. As it approaches, Jupiter's gravitational pull synchronizes with the asteroid's orbit. If this synchronization falls within the Kirkwood gap, the asteroid experiences repeated pulls, pulling up slightly each time it completes its orbit. Eventually, these jolts can shift the asteroid's orbit, pushing it out of the resonance gap into a less perturbed region, where Jupiter's influence is less synchronized with its orbit. In the outer part of our solar system, beyond the gas giants and the icy Kuiper Belt, lies another fascinating story of celestial harmony. Neptune, the 8th planet from the Sun, and Pluto, a dwarf planet in our system that was once considered the 9th, have a unique gravitational relationship that defies the odds of collision. This relationship is determined by the 3-to-2 resonance gravitational lock, which ensures that for every 3 revolutions of Neptune around the Sun, there are 2 revolutions of Pluto. This rhythmic interaction is not just a coincidence. The influence of this resonance is profound, shaping their orbital trajectory so that, despite their overlapping orbits, Neptune and Pluto never collide. Pluto's orbit, influenced by this resonance, is markedly eccentric and tilted as it winds above and below the plane of the solar system, balancing over millennia. This harmonious arrangement emphasizes the complex laws of physics that ensure stability and order in the vastness of space. But what do all these things have in common? The satellites, the planets themselves, their rings and asteroid belts. And why are only some of them affected by orbital resonance? The answer lies in the subtle interplay of celestial mechanics, where eccentricity, inclination, and gravitational forces come together. Orbital resonance is based on 3 key factors: eccentricity, a measure of the elongation of an orbit; inclination, the tilt of an orbit relative to a reference plane, whether concerning a star or another celestial body; and gravitational forces, which tie everything together. These elements are intertwined, determining whether a body falls into the grip of orbital resonance or avoids it. When a celestial body falls into resonance, its orbit becomes locked in a gravitational interaction with another body, usually a much larger one. This fixation can increase stability, as seen with Neptune and Pluto. However, there are simultaneous exceptions in which objects will be ejected from their trajectories, cutting gaps in regions such as the asteroid belt. The role of eccentricity and tilt in this process cannot be underestimated. A small increase in eccentricity, for example, can dramatically change the gravitational interaction of a body, bringing it into or out of resonance. Similarly, inclination can tilt an orbit so that it interacts with the gravitational influence of another body at just the right point to enter resonance. This complex balance of forces makes orbital resonance a selective phenomenon, affecting only those bodies that meet the precise conditions necessary to synchronize with the rhythm of their larger neighbors. It's a cosmic lottery where the prize is a stable orbit or, in some cases, total expulsion from the system. Looking beyond our solar system, we discover how the action of orbital resonance plays out on a grand cosmic stage, determining the fate of exoplanetary systems across the universe. These distant systems, with their unique clusters of planets, offer a fascinating glimpse into the complex design of the celestial mechanics that govern them. Observations of these distant worlds have revealed cases where the planets keep pace with each other, their orbital periods maintaining an exact relationship. One striking example is the TRAPPIST-1 system, where several Earth-sized planets are locked in a complex chain of resonances. Such configurations raise intriguing questions about the formation and evolution of planetary systems, challenging and refining our theories. Meanwhile, the major planets of the solar system themselves do not show a clear pattern of orbital resonance with each other. Their orbital periods don't have a simple integer ratio that would indicate resonance. While there are close resonances, such as the 5:2 resonance between Jupiter and Saturn, they're not as precise or stable as resonances between some moons, or in more dynamically bound systems such as Pluto and Neptune. The implications of these observations go far beyond simply cataloging celestial phenomena. They provide insight into the processes governing planet formation and suggest that resonances may play a key role in the assembly of planetary systems from protoplanetary disks orbiting young stars. As we continue to observe and study such phenomena, each new study peels away another layer, revealing the intricate plan of the universe, bringing us closer to unraveling the fundamental principles that govern celestial motion and illuminating the very essence of our existence. In the 21st century, humanity finds itself at a crossroads at a moment in history when we can see the stars, but not yet touch them. Born in the era between exploring our own planet and the possibility of reaching other worlds, we stand on the threshold of an extraordinary journey. It's not just about rockets or physics, but about our survival and our place in the universe. Imagine a future in which Earth faces an existential threat, a catastrophic collision with an asteroid, a climate collapse, or something completely unforeseeable. Our solution? Build generation ships, colossal spaceships that serve as floating cities where multiple generations are born, live, and die while traveling to another star, to a new home. Einstein's special theory of relativity tells us that traveling faster than light is impossible. However, space is within our reach, even at a speed that is only a fraction of the speed of light. Generation ships traveling at a significant fraction of light speed could travel vast distances between stars. With technology such as matter-antimatter engines, compact fusion drives, and even black hole propulsion, what seems like science fiction could become a reality. But these ships are not just vessels. They are lifeboats for humanity. They must sustain life for centuries, perhaps millennia, facing the challenge of space travel, genetic diversity, and mental health. Each ship will be a microcosm of Earth, with its social structures, cultural heritage, and daily challenges. What would it take to build such a ship? How can its inhabitants survive and thrive? Join us as we delve into the intricacies of interstellar travel without exceeding the speed of light. Today, we'll try to unlock the secrets of how humanity can one day travel to the stars, but not in an instant, but through generations. Planning for interstellar travel is not only about technology, but also about predicting why such travel might become necessary. Foreseeable threats to humanity's survival may force us to seek refuge outside our solar system. Understanding these threats will help us prepare for possible future scenarios that could force humanity to embark on such an extraordinary journey. One of the most immediate threats comes from space itself: comet impacts. Throughout Earth's history, collisions with comets and asteroids have caused mass extinctions and major climate shifts. A strong enough collision could make Earth uninhabitable, forcing us to seek a new home among the stars. Another serious threat is climate collapse. Human activity has already led to significant changes in our climate: rising temperatures, melting polar ice caps, and increasingly severe weather events. If these trends are not controlled, Earth could become hostile to human life, making searching for habitable exoplanets a top priority. Technological progress, while bringing enormous benefits, also carries significant risks. Advances in artificial intelligence, biotechnology, and autonomous systems could lead to scenarios where humanity faces a threat from its own creations. Uncontrolled AI or engineered pathogens could become existential risks, leading to the need to establish human colonies on distant worlds as a defense of our species. In search of a new home, Proxima Centauri b is a prime candidate. Located just 4.24 light-years away in the Alpha Centauri system, it is the closest known exoplanet that's in the habitable zone of its star. As many know, this zone, often referred to as the Goldilocks zone, is the area around a star where conditions may be optimal for the existence of liquid water, an essential ingredient of life for humanity. Proxima Centauri b was discovered in 2016 and has been the subject of intense study ever since. It orbits a red dwarf star that's smaller and colder than our Sun, meaning the planet would have to be much closer to its star to be in a habitable zone. This proximity, while favorable for retaining heat, also exposes the planet to flares and radiation, which must be considered when planning human habitation. Current research indicates that the planet has a mass similar to Earth's and may have a rocky surface. However, much about it remains unknown, including the composition of its atmosphere and the presence of liquid water. Future missions and observations will be needed to collect more data and assess its suitability for life. Sending a spacecraft to our nearest neighboring star involves not only covering the distance, but also ensuring that the distance is suitable for human life. This requires a multifaceted approach that includes robotic probes and telescopes to gather detailed information about the planet's environment. These missions will help determine the feasibility of establishing a human colony and the preparations necessary for long-term survival. Proxima Centauri b was chosen as our target because of its relative proximity and potential habitability. However, reaching and inhabiting the distant world will be a monumental task requiring an unprecedented level of planning, innovation, and collaboration. The dream of exploring the stars has always been tempered by the harsh realities of physics and time. Traditional concepts of space travel, where one crew sets off and reaches their destination within their lifetime, seem increasingly impractical when it comes to the vast distances between the stars. This is where the concept of intergenerational ships come into play, a bold and innovative solution to the problem of long-distance space travel. Generational ships, also known as intergenerational or generation ships, are designed to keep people alive for centuries or even millennia. These ships are self-sustaining ecosystems with not only one crew on board, but all of their descendants. Life on a generational ship is designed to mimic a small self-contained world with living quarters, food production, water recycling, and social systems. The concept is simple, yet profound. As the original crew ages and eventually passes away, their children and their children's children continue the mission. This life cycle ensures that for many generations, the ship will continue its journey, and each new generation will be trained and prepared to maintain the ship and eventually reach its destination. This approach to space travel requires careful planning and robust systems to ensure that the inhabitants survive and thrive. Every aspect of life must be carefully considered, from genetic diversity to ensure a healthy population, to cultural and educational programs that preserve and pass on vital knowledge and skills. Einstein's special theory of relativity presents a serious problem for traveling faster than light. According to this theory, as objects approach the speed of light, their mass increases and they require exponentially more energy to continue accelerating. This effectively makes traveling faster than the speed of light impossible with our current understanding of physics. Generational ships offer a practical solution within the framework of Einstein's theory. By accepting the duration of space travel and planning for generations of life aboard such ships, humanity can aspire to distant stars. Such an approach recognizes the limitations imposed by the theory of relativity, while at the same time supporting the resilience and adaptability of the human spirit. Traveling to the stars requires overcoming significant challenges, not the least of which is the vast distance between celestial bodies. To make interstellar travel feasible within a human lifetime, we have to take a closer look at the advanced propulsion techniques and the intriguing phenomenon of relativistic time dilation. Relativistic time dilation is a consequence of Einstein's special theory of relativity. When an object approaches the speed of light, time on board is slowed down compared to the time experienced by an observer at rest. This means that for a spacecraft traveling at a significant fraction of the speed of light, the travel time of the crew will be shortened compared to those who remain on Earth. For example, if a ship could travel at 90% of the speed of light, time dilation would cause 1 year aboard the ship to be equivalent to more than 2 years on Earth. Because of this effect, interstellar journeys stretching over decades or centuries may seem shorter to the crew, although they do not shorten the actual distance. Several advanced propulsion methods have been proposed to achieve the high speeds required for interstellar travel. Each method has its own set of problems and potential advantages. For example, antimatter propulsion involves the annihilation of matter and antimatter with the release of enormous amounts of energy. This reaction releases energy much more efficiently than chemical rockets, potentially allowing spacecraft to reach significant fractions of the speed of light. However, producing and storing sufficient antimatter remains a major technical hurdle. On the other hand, compact fusion reactors use nuclear fusion, the same process that powers the sun to produce energy. By combining light atomic nuclei, such as hydrogen, with heavier nuclei, these reactors could provide sustained and powerful thrust for spacecraft. While controlled fusion technology is promising, it's still under development, and building a compact and reliable reactor suitable for spaceflight is another major engineering challenge. Black hole propulsion is a more speculative concept that involves harnessing the enormous gravitational energy of a black hole to propel a spacecraft. The idea is a small artificial black hole and harness the energy of the Hawking radiation it emits. Theoretically, this method could provide continuous and powerful acceleration, but the technology to create and control artificial black holes is still in the realm of something fantastic, far beyond our current capabilities. However, the problems don't end with thrusters. Traveling at near light speed is fraught with many dangers. One of the main ones is the threat posed by interstellar particles. At these high speeds, even tiny particles can cause significant damage in a collision. Spacecraft must be equipped with advanced shielding to protect against these high-energy collisions. Radiation is another serious hazard. High-speed space travel exposes the crew to intense cosmic radiation that can have deleterious health effects. Effective radiation protection and possibly even medical intervention will be a necessity to keep the crew healthy during long-duration missions. Maintaining the structural integrity of the spacecraft over the long term is also critical. The stresses and strains of high-speed flight can weaken materials over time, requiring advanced construction techniques and regular maintenance to keep the spacecraft safe and functional throughout the voyage. Despite these formidable challenges, the pursuit of interstellar travel drives human ingenuity and ambition. By researching and developing advanced propulsion techniques and overcoming the dangers of high-speed travel, we're taking crucial steps toward reaching for the stars and expanding our presence in space. Choosing the right propulsion system for interstellar travel is one of the most important decisions in mission planning. The propulsion system determines the speed, duration, and feasibility of the mission, so it's important to explore both best practices and traditional methods. One promising approach is to scale up the traditional propulsion technologies. NASA's Parker Solar Probe uses a combination of chemical propulsion and gravitational assists to achieve unprecedented speeds. The probe is traveling at more than 430,000 miles per hour, which is approximately 0.064% of the speed of light and makes it the fastest man-made object to date. Its propulsion system is based on hydrazine thrusters, powered by solar energy, which showed the potential of using existing technology for high-speed space travel. Gravitational assists, or slingshot maneuvers, use the gravity of planets or other celestial bodies to increase the speed of a spacecraft without expending additional fuel. By carefully planning a trajectory, a spacecraft can gain significant speed, reducing travel time over vast distances. This technique, while insufficient by itself for interstellar travel, can be an important component of a multi-stage propulsion strategy. Scaling up these traditional technologies involves developing more efficient thrusters and larger amounts of fuel. Another promising area is innovation in ion thrusters, which use electric fields to accelerate ions and create thrust. Ion thrusters are highly efficient and can operate for long periods, making them suitable for long-duration missions. The combination of these advanced conventional methods could be a practical solution for the initial stages of interstellar travel. For faster travel, we must consider more advanced propulsion methods, such as nuclear propulsion. One of the most intriguing concepts in this category is the Orion project, first proposed in the 1950s. This method involves a series of thermonuclear explosions behind the spacecraft, each of which creates a powerful thrust to propel the spacecraft forward. The Orion project uses a massive pusher plate at the rear of the spacecraft, designed to absorb shock waves from explosions and convert them into forward momentum. By repeating this process in a controlled manner, the spacecraft will be able to reach significant fractions of the speed of light, drastically shortening the flight time to nearby stars. Although the concept is theoretically sound, many technical and safety problems still have to be solved. Controlling the timing and directions of explosions requires precise design, and the spacecraft in turn must be designed to withstand enormous loads. In addition, the environmental impact of launching such a vehicle from Earth must be carefully considered, which may also require space launch platforms. Another fusion engine concept is the Daedalus project, which involves using fusion reactions to propel a spacecraft. This method involves the use of small pellets of fusion fuel, such as deuterium and helium-3, which are ignited by electron beams to create a constant thrust. The Daedalus project aims to reach speeds of up to 12% of the speed of light, which would make it possible to travel to the nearest stars within a human lifetime. Fusion propulsion offers a more controllable and potentially safer alternative to the Orion method. However, the technology to build reliable and efficient fusion reactors for spaceflight is still under development. Significant advances in fusion research and engineering are needed to make this approach viable for interstellar missions. Choosing the right propulsion system is a balance between feasibility, safety, and performance. Traditional methods, such as those used in the Parker Solar Probe, offer practical short-term solutions, while advanced fusion propulsion concepts such as the Orion and Daedalus projects promise the potential for faster and more ambitious interstellar travel. Ensuring the survival and health of the crew over multiple generations is a cornerstone of generational ship planning. One of the most important aspects is maintaining genetic diversity, which is necessary to prevent inbreeding and genetic diseases that could jeopardize the mission. To solve the problem of genetic diversity, scientists use Monte Carlo simulations. These models use statistical methods to simulate and predict genetic variability over many generations. By introducing various parameters such as initial population size, mutation rates, and reproductive patterns, these simulations can provide insight into the genetic health of a population over time. Monte Carlo simulations help determine the minimum population size needed to maintain genetic diversity and prevent inbreeding depression. They also take into account possible random events, such as accidents or disease, that could affect the population. Such modeling is essential to creating a sustainable human colony that can thrive for centuries. Maintaining genetic diversity requires careful planning of reproductive strategies and potential genetic screening. The crew must be educated about the importance of genetic health and the steps necessary to maintain it. This includes monitoring genetic diversity and making informed decisions about partnership and reproduction. Research shows that a minimum initial population of at least 100 individuals is required to maintain genetic health over several generations. This figure comes from studies by scientists such as Frédéric Morin and Camille Boullouffi, who have extensively studied the genetic dynamics of small isolated populations. In their research, Morin and Boullouffi use Monte Carlo simulations to explore different scenarios, including different population sizes and reproductive strategies. Their study shows that with a balanced sex ratio and optimal reproductive rate, an initial population of at least 100 individuals can maintain a healthy gene pool. This population size ensures that genetic drift and inbreeding will not jeopardize the health and viability of future generations. An initial population of 100 individuals should grow to 500 individuals over several generations. This growth is necessary to create a stable and resilient population that can cope with unforeseen challenges. The modeling takes into account various factors, such as random genetic mutations, environmental influences, and possible catastrophes to ensure the sustainability of the population. Designing a generational ship to accommodate a growing population involves planning for adequate living space, resources, and social structures. The ship should provide educational, health, and recreational facilities to support the physical and mental well-being of the crew. And this includes collaborative activity spaces and private living quarters to provide a balance between social interaction and personal privacy. Beyond the physical infrastructure, it's vital to maintain social cohesion and cultural continuity. The crew must develop a shared sense of purpose and identity to foster cooperation and sustainability. Cultural and educational programs play a key role in maintaining the knowledge and values necessary for mission success. Effective crew and population planning is essential to the success of a generational ship. Using advanced genetic simulations and research, we can ensure that the population remains healthy and viable. With careful planning and a commitment to maintaining social and genetic health, humanity can thrive on the path to the stars, ensuring the survival and prosperity of future generations. Above all, however, designing a generation ship capable of sustaining human life for centuries involves creating a self-sustaining environment that mimics the basic aspects of life on Earth. This includes creating artificial gravity, producing food, and recycling vital resources such as water and air. These systems must be reliable, efficient, and able to operate autonomously for long periods. One of the most important aspects of ship design is the creation of artificial gravity to maintain the health and wellness of the crew. Prolonged exposure to microgravity can lead to muscle atrophy, loss of bone density, and other health problems. To counteract these effects, generation ships can use rotating media to create a centrifugal force that mimics Earth's gravity. The most practical design involves a large rotating ring or cylindrical section where the crew lives and works. As the structure rotates at a certain speed, centrifugal force pushes the occupants outward, simulating the effect of gravity. example, a ring with a radius of 100 yards must rotate at a rate of about 3 revolutions per minute to create an artificial gravity of 1 g, similar to Earth's. This design not only helps maintain physical health, but also provides a familiar environment that can alleviate the psychological challenges of living in space. Rotating habitats can include living quarters, recreational areas, and workspaces designed to optimize the use of available space and resources. Reliable and efficient food production systems are also required to sustain populations for generations to come. Hydroponic and aeroponic systems offer solutions for growing crops without soil, using nutrient-rich water or mist to nourish the plants. These methods are highly efficient, use less water and space than traditional farming, and are well suited to the controlled environment of our ship. Hydroponic systems involve growing plants in nutrient solutions with their roots suspended in water. Aeroponic systems, on the other hand, use a fine mist to deliver nutrients directly to the roots. Both systems can grow a wide range of crops, from leafy greens to root vegetables, providing balanced nutrition for the crew. These systems can be automated and monitored to maintain optimal growing conditions, ensuring a stable and reliable food supply. In addition, genetic modification and breeding will be able to increase the yield and nutritional value of crops. Efficient water and air recycling is critical to the sustainability of a generation ship. Water recycling systems must be capable of recovering and treating wastewater, ensuring a continuous supply of clean water for drinking, cooking, and irrigation. Advanced filtration and purification technologies, such as those used on the International Space Station, are already achieving high levels of efficiency. On the ISS, for example, the water reclamation system can recycle up to 98% of wastewater, including urine and sweat. This level of efficiency is necessary for long-duration missions when resupply from Earth is not feasible. Ships of future generations will need to improve this efficiency even further, aiming for near-complete recycling to minimize the need for large water reserves. Air recycling is equally important, requiring systems that can remove carbon dioxide and replenish oxygen. Natural systems, such as photosynthesis in plants, can be integrated with artificial CO2 scrubbers to maintain a balanced atmosphere. Plants, in turn, not only provide oxygen but also contribute to the psychological well-being of the crew by providing a connection to nature. Projects such as Biosphere 2 have demonstrated the potential for creating closed ecosystems in which plants, humans, and microorganisms coexist by recycling air, water, and nutrients. Although Biosphere 2 faced some challenges, it demonstrated the feasibility of such systems, providing valuable lessons for the design of life support systems on generational ships. Creating a self-sustaining generational ship requires integrating advanced technology with natural processes to ensure the health and well-being of its inhabitants. Artificial gravity, efficient food production, and reliable disposal systems are the very pillars of this design, enabling humanity to embark on a long-term journey to the stars. Ensuring the success of a multi-generational mission goes beyond the physical and technological aspects of the ship. It requires meeting the mental, social, and educational needs of the crew, ensuring their health, motivation, and cohesion throughout the long voyage. Isolation and confined spaces can significantly affect morale and mental health. Lack of new stimuli and prolonged separation from Earth can lead to feelings of loneliness, depression, and anxiety. Addressing these issues is critical to maintaining a stable and motivated crew. Virtual reality technologies offer promising solutions for mental health and cultural connection. By creating immersive simulations of terrestrial environments, virtual reality or VR can provide a sense of escape and familiarity. Crew members will be able to see forests, oceans, and even social gatherings, helping to alleviate feelings of isolation and to maintain a connection to their home planet. Artificial intelligence can also play an important role in supporting crew mental health. AI therapists, such as NASA's Simon 2.0, can offer individual counseling, monitor psychological well-being, and suggest strategies for coping with stress and interpersonal conflict. These AI systems can adapt and learn from each generation, providing continuity and consistency in mental health support. Ensuring the intergenerational transfer of knowledge and skills is critical to mission sustainability. A comprehensive education system must be put into place to ensure that each new generation receives the necessary skills to operate and maintain the ship, as well as the knowledge to continue research and exploration. This should include formal education, practical training, and the preservation of cultural and historical knowledge. Embarking on an interstellar voyage requires not only technological prowess, but also a deep commitment to the human spirit. By addressing the mental, social, and educational needs of the crew, we ensure the resilience and connection of each generation that carries the torch of exploration and survival. Advanced technologies such as virtual reality and artificial intelligence support, combined with strong cultural and social structures, will create the foundation for a thriving community across generations. When we reach beyond our solar system, a harmonious blend of innovation and humanity will lead us to new worlds, securing our future as an interstellar species. In the vast theater of our solar system, where planets like Jupiter and Saturn often attract attention with their majestic rings and violent storms, lies a distant world shrouded in mystery and intrigue. This is Uranus, an enigmatic ice giant that often goes unnoticed, but holds secrets that may unravel some of the most enduring mysteries of the cosmos. Far beyond the asteroid belt, nestled between the orbits of Saturn and Neptune, Uranus travels through the cold and dark corners of our solar system. It's a world that lives at a different rhythm, spinning on its side, an oddity that's long puzzled astronomers and spawned countless theories. Discovered in 1781 by William Herschel, Uranus was the first planet discovered through a telescope, extending the known boundaries of our solar system. For centuries, this distant world was just a speck of light in our telescopes, a ghostly blue ball, distant and aloof, keeping its secrets. But now, with the advent of the James Webb Space Telescope, a new chapter in the exploration of Uranus is opening. JWST, with its unprecedented vision, peels back the layers of this icy giant, revealing a world of amazing beauty and complexity. Let's travel together to this mysterious ice giant and learn about the latest discoveries made by the James Webb Space Telescope. In the quest to understand the universe, humankind has launched a Sentinel into space, a marvel of engineering and a testament to our insatiable curiosity. This Sentinel is the James Webb Space Telescope, the most advanced and powerful space telescope ever built, the successor to the legendary Hubble Space Telescope. Equipped with a set of advanced instruments and a mirror more than 6.5 meters in diameter, JWST is designed to observe the universe in light invisible to the human eye, the infrared spectrum. This allows the telescope to peer through clouds of cosmic dust, discover distant galaxies, and study the atmospheres of exoplanets. The telescope's journey into space was a feat in itself. Launched on an Ariane 5 rocket, JWST traveled to a point in space known as the Second Lagrange Point, or L2, 1 million miles from Earth. Here, in this stable orbit, JWST can observe the universe with minimal interference from Earth and the Sun. JWST's capabilities are not limited to observing the early universe or distant galaxies. it plays a key role in unlocking the mysteries of our solar system. Its powerful instruments, such as the Near-Infrared Camera, NIRCam, and the Mid-Infrared Instrument, MIRI, reveal new details about planets, moons, and other celestial bodies closer to home. Take Uranus, for example. In the past, our view of this distant planet was limited to faint images from telescopes such as Hubble. But now, thanks to JWST's enhanced infrared capabilities, we can see Uranus in a new light. The telescope's sensitive instruments allow us to observe the planet's atmosphere, weather patterns, and even its mysterious rings with unprecedented clarity. By analyzing the light of Uranus, JWST can decipher the chemical composition of its atmosphere, revealing the presence of gases such as methane and hydrogen. This not only helps us understand the current state of Uranus, but also provides clues about its formation and evolution. The James Webb Space Telescope continues to exceed expectations, revealing more details about our universe every day. Its latest triumph is a series of images of Uranus taken very recently, surpassing even the stunning observations made in April 2023. In early 2023, JWST provided us with unprecedented views of Uranus, allowing us to look at the planet's atmospheric dynamics and ring system in a new light. The recent images, however, are a step further. Not only are they clear, they reveal aspects of Uranus that were previously hidden or obscured, even in April observations. Take the rings of Uranus, for example. The latest images show them with even greater clarity. We can now observe finer structures within the rings and even detect faint dust bands that were previously invisible, such as the Zeta ring, the incredibly thin ring closest to the planet. The strength of JWST lies not only in its one-off observations, but also in its ability to continuously track celestial objects. Continuous observations of Uranus have allowed us to observe changes in the planet's atmosphere, track the movement of its clouds, and observe the evolution of its storms over time. The changes in the polar regions are particularly striking. Bright white caps and dark bands near the poles, the origin of which is still unclear, have shown marked changes. This continuous observation provides invaluable data for understanding the seasonal changes and long-term climate patterns of Uranus. In the set of planets in our solar system, Uranus stands out with a peculiar feature, an extraordinary axial tilt. Unlike any other planet, Uranus rotates practically on its side, tilted at an angle of about 98 degrees. This unique orientation has long intrigued astronomers and sparked a quest to understand its consequences. To understand the significance of this tilt, we must travel back in time to the early days of our solar system. Uranus probably formed with a much less severe tilt. The prevailing theory suggests that a catastrophic event, perhaps a collision with a planet-sized object, dramatically changed its orientation. This colossal impact would have thrown Uranus aside, changing the definition of its axis of rotation. Such a dramatic event in the planet's history probably not only changed its rotation, but also left an indelible mark on its entire system, including its satellites and rings. Today, this lateral rotation is a unique spectacle. Each pole of Uranus is alternately flooded with sunlight and plunged into darkness at intervals of 42 years. This extreme tilt results in extreme seasons, unlike those observed on other planets. The implications for planetary observations and research are enormous. Uranus's tilt allows us to observe its rings and satellites from different perspectives, offering insights into their composition and dynamics. For example, when Uranus's rings face the Earth, they become nearly invisible, exposing fainter dust bands and smaller satellites. Compare that to Earth, which is tilted only 23.5 degrees. Uranus's extreme tilt causes drastic changes in its weather patterns, which is a goldmine for scientists studying planetary climate. Tilt also affects the circulation of Uranus's atmosphere, prolonged exposure to sunlight at the poles can result in complex weather systems, as seen in recent JWST images. These systems are very different from those on other planets and provide a unique laboratory for understanding atmospheric physics. Let's take a journey on one Uranian year. Each season on Uranus lasts about 21 Earth years, a consequence of its 84-year orbit around the Sun. This extended duration means that each hemisphere experiences long periods of daylight, followed by equally long nights. As a result, the planet undergoes dramatic changes in appearance and climate. Because one pole of Uranus basks in uninterrupted sunlight, summers are long, while the opposite pole plunges into a deep, dark winter. This stark contrast creates unique atmospheric conditions, causing complex weather patterns and climatic shifts. The impact of these seasonal changes on Uranus's atmosphere is profound. When the sun illuminates the planet's surface, it warms the atmosphere, creating colossal storms and dynamic cloud systems. These atmospheric phenomena are not static. They evolve and change with the seasons, painting an ever-changing portrait of the planet. Among the most striking features are the bright cloud tops that appear when the sun illuminates the planet's atmosphere. These clouds, composed of frozen methane and other gases, reflect sunlight, creating a dazzling spectacle. Conversely, dark storm patches that look like giant hurricanes roam the planet's surface. Moreover, the planet's seasonal phenomena affect not only the planet itself, but also its moons. One recent study of Uranus's moons, or rather a phenomenon that's particularly intriguing, is the development of temporary atmospheres on these moons, a spectacle caused by the unique conditions of the Uranus system. The key to understanding these temporary atmospheres lies in the extreme tilt of Uranus's axis and its effect on the satellite's orbits. As these satellites orbit the planet, they experience dramatic changes in solar exposure, alternating between long periods of intense sunlight and prolonged darkness. During the long summer exposed to sunlight, the icy surfaces of these satellites undergo a process known as sublimation. The ice, composed mainly of water, methane, and carbon dioxide, transforms directly from solid to a gas, bypassing the liquid phase. This sublimation creates thin, temporary atmospheres, or exospheres, that envelop the satellites. These exospheres are most pronounced when moons are warmest. Recent research by the James Webb Space Telescope shows that this phenomena is more dynamic and complex than previously thought. Exospheres are heterogeneous. They vary in composition and density, depending on the topography of the moons and the intensity of solar radiation. As the satellites enter their winter phase, the exospheres gradually dissipate. Gases recondense on the surface, returning to an icy state. This cycle of atmosphere creation and disappearance is a unique characteristic of Uranus's satellites, opening a window into the interaction between solar radiation and surface ice. The rings of Uranus, often overshadowed by the majestic rings of Saturn, hold their own tale of cosmic intrigue and dynamism. A recent comparative study of the rings of Uranus, Saturn, and Jupiter sheds new light on these lesser-known but no less fascinating celestial features. In contrast to the wide and bright rings of Saturn, the rings of Uranus are narrow, dim, and less extensive, extending to 4 planetary radii. This includes elusive rings, such as the Mu and Nu rings. The study delves into the gravitational influence of Uranus's main satellites on these rings, a key factor in their formation and evolution. The significant influence of Uranus's 5 major satellites, Miranda, Ariel, Umbriel, Titania, and Oberon, plays a central role in the history of the rings. These satellites, much more massive than their smaller counterparts, dominate the gravitational dynamics within the Uranus system. Their positions and masses relative to Uranus provide a better understanding of the formation of the satellites, and the gravitational formation of the rings. The formation of Uranus's rings is attributed to a combination of processes, including collisions, satellite breakup, and gas release from the main satellites. These dynamical processes affect the material composition of the rings and are influenced by the ever-changing environment of the Uranus system. The stability of the rings is intrinsically linked to their dynamical interactions with the satellites of Uranus. The study examines how accretionary processes occur within the Roche limit and how the dynamics of shepherding moons play a crucial role in maintaining the rings. In addition, the rings provide a unique opportunity to understand the internal structure of Uranus through seismological studies. Modeling results show how these satellites shape the ring system, affecting its structure and stability over time. The modeling predicts significant material loss within the ring system, primarily due to gravitational interaction with the satellites. The complex dance between moons and rings is a key aspect of the Uranus system. The dynamic exclusion zones created by the satellites and the influence of these zones on the material distribution of the rings are crucial to understanding the structure and the evolution of the rings. The study also examines the role of satellite-to-satellite interactions in the evolution of the system, especially past resonances between satellites such as Ariel and Umbriel, and their impact on the orbits and geology of satellites, especially Miranda. But the mysteries surrounding this planet don't end there. You've probably heard of the Aurora Borealis. Well, the latest discovery concerns the auroras of Uranus, which also has them. However, its auroras, unlike Earth's, occur in the infrared spectrum. Using the Keck 2 telescope, astronomers observed enhanced emissions of trihydrogen cation in the planet's atmosphere. This is a groundbreaking discovery that sheds light on the unique magnetic field and dynamics of Uranus's atmosphere. Uranus's magnetic field, which is significantly deflected from the planet's axis of rotation, creates a unique coupling of the magnetosphere, ionosphere, and thermosphere. The detection of these infrared auroras is crucial because it opens up a new window into these processes, previously elusive due to the lack of such detections on Uranus. Comparing the polar auroras of Uranus with those of Jupiter and Saturn reveals their different characteristics. Unlike Jupiter, where the H3+ emissions have short lifetimes that smooth out the variability of the UV emission, the brightest infrared emissions of Uranus do not necessarily coincide with the brightest UV emissions of the other planets. This unique aspect of Uranus's polar lights provides valuable information for exoplanet studies, especially for the worlds of warm ice giants. The study delves deeper into the unusual heat spots on Uranus, observed near the latitudes of the UV northern lights. These spots, analyzed for temperature, column density, and total emission, suggest that the enhancement is not caused by temperature, but rather by increased ionization, probably due to polar aurora activity. Polar lights play a significant role in heating the atmosphere, and on Uranus, the increased H3+ emissions associated with these auroras suggest their involvement in atmospheric processes. By studying such unique things, we gain a deeper understanding of similar processes in different planetary environments, enriching our knowledge of how auroras shape planetary atmospheres, affecting not only thermal properties, but also the overall dynamics of the ionosphere and magnetosphere. In the quest to unravel the mysteries of our solar system, the ice giants Uranus and Neptune are distant enigmas beckoning closer exploration. Recent research, including a fresh analysis of Voyager images, has revealed that the two planets actually have similar shades of greenish-blue color, fundamentally changing our long-held beliefs. Uranus and Neptune share many common characteristics. They're roughly the same size, have the same mass, and are surrounded by deep atmospheres of comparable materials. Nevertheless, it was long thought that their appearance was quite different. This misconception has now been corrected. Both planets are shown in their true colors, largely influenced by the methane layer in their atmospheres. The need for a dedicated mission to Uranus has never been greater. Such a mission would not only deepen our understanding of the planet itself, but also provide a comparative view of Neptune and other similar icy giants. The mission's potential goals range from studying the unique magnetic field and complex ring system to investigating atmospheric dynamics and internal structure. In an important achievement for planetary exploration, the Uranus Orbiter and Probe mission has been elevated to the highest priority for NASA flagship mission within the 2023-2032 Planetary Science Decadal Survey. Future launch windows are available between 2030 and 2034. Key science goals will include a detailed analysis of the unusual tilt of Uranus's axis and its effect on the planet's climate and weather patterns. The mission can also study the intriguing phenomena of infrared auroras and their role in heating the atmosphere, providing a comparative study with other planets. Studying Uranus and Neptune will also provide valuable information about planetary evolution and dynamics. Understanding why Uranus appears slightly whiter, perhaps due to its more stagnant atmosphere, allowing methane haze to accumulate, can tell us a lot about atmospheric processes on the ice giants. As we await a future mission to Uranus, we stand on the threshold of discoveries that could redefine our understanding of the outer solar system. Exploring this distant ice giant will not only unravel its mysteries, but will also expand our knowledge of planetology as a whole, shedding light on the complex picture of our cosmic home.